we start with a group G, and you can assume that this group G, for example, is SLN, or in some situations you can say projective linear group. The important input is that we have some surface. So on the one hand side, we can have a Riemann surface. And so it's something like that. And so it comes with punctures. I also assume that we have punctures. And actually, later on, it could be maybe even more general than this. Maybe you have some hole, and on this hole you have something else. But let's just talk in the case, suppose you have punctures. So this is my Riemann surface. And this is a completed surface minus some finite number of punctures. Okay, then another data will be exactly as in Bertrand talk. So you have assigned to this punctures, you have some lambdas, or maybe it is alphas. And so for me, this will be elements of the dual Lie algebra. So I follow basically notations of Bertrand's talk, so except that it's alpha, not lambda, not alpha. So H is a Cartan Lie algebra of Cartan Lie group of G. All right, then there is a construction which takes this as an input and produce out of this some vector space. So I call the space of coinvariance, and people can call the space of conformal blocks or dual to the space of conformal blocks. I'll call space of coinvariance. And I'm not going to give you this definition, but just say that there is some vector space, coinvariance, which starts from this Riemann surface sigma, and use this Lie algebra. So the group G has Lie algebra, this G, and then there is something W algebra. Doesn't matter what this is. For GL2, SL2 is Virasoro algebra. So it takes as input of some representations of this guy, Verma modulus, assigned to those points. And so you kind of imagine that there is this lambdas sits over these points, and then produce some vector space. I'm not telling you what the definition of this vector space is, who are those coinvariants, but what's important is that these guys are the lambda. The lambda are this highest weight modulus. Again, maybe you don't want to know what this is, but what is really important is that they have one distinguished vector, V lambda, and then there are many other vectors underneath, and it's infinite dimensional. And so, in particular, in this space, you can take the product of those vectors, tensor product, and it gives you some vector which lives in the space of coinvariance. It projects to something in coinvariance. Okay. So that's on the one hand side. Now, on the other hand, maybe I should put the other hand here. This is like on the day side, on the night side, there is something entirely different. So, first of all, you start with topological surface S. And how this topological surface relates to this one, the relation should be such that if you take this Riemann surface, and I would take, say, complex points of this Riemann surface, really Riemann surface, then this is diffeomorphic to this S. So you start with that, and then you can assign to this some space. Okay, I use this notation for this space. But what it is the space of flat G connections on this topological surface S up to isomorphisms. And this is a very, very easy thing. So you just take all possible, because you have punches, you have this free group, the fundamental group of S, and you consider all possible maps of this group to your complex group. So you take the space of all homomorphisms, and you consider its modular conjugation. So you can simultaneously conjugate representations like that. And so this is the same as the space of flat connections, because if you have the surface, some kind of surface, and you have some kind of flat connection over the surface, so you can consider parallel transport, and then you get representation of the fundamental group and the fiber of your space. So that's what it is. And then the idea on the right-hand side is that it's supposed to produce, and actually it does produce, this quantization space. So So what is this quantization space? So it's a Hilbert space. Let's have a name for the space, H, G, S, it depends on that. And it has a number of additional structures, but in particular this, the group gamma S. So gamma S is a mapping class group. So this mapping class group of S is supposed to act on this Hilbert space by unit transformations, but this is not yet the complete data. There is more to say about this. But no matter how you get this quantization space, and so we have this quantization space, that's okay. We have it, check. But then comes a conjecture. Well, do you still see, or maybe I go to that side? There is this conjectural vector. And it's not actually a vector in this space, but it's almost like a vector in this space. Let me have a name for this, C sub E, which lives in some sense, it's not exactly true, in this Hilbert space. And the main kind of thing is that this guy and this guy, they are related. Is there anywhere close to be understood what I'm talking about, or this is completely... Yes?
In the left-hand side, how this surface interferes. In the left-hand side, it's pure representation. Looks
on the right-hand side, it's pure representation zero. On the left-hand side, it depends on Riemann surface.
How?
I didn't say what is coinvariance, but imagine that you, in the case of SL2, then at every puncture you put some representation of Virasoro algebra. It's basically the algebra of vector fields on the circle extended, a one-dimensional space, and then you consider tensor product of those representations of Virasoro algebra, and then you take coinvariance. So there is a construction that if you have a representation of any algebra or Lie algebra, L, if takes in some vector space, you can take coinvariance, take modulo all kind of vectors like that. So this is a space of coinvariance of the action of the Lie algebra on the vector space. And I take coinvariance with respect to, I consider roughly speaking, some meromorphic vector fields on the sigma. Meromorphic with poles at the punctures, so they act on the standard product of these representations of Virasoro algebras, because each of these vector fields, so you have a surface, and if you take a puncture, so there's a little circle here, and your vector field gives you some vector field on the circle, and so basically it's in Virasoro, and I take co-invariance. So I embed this Lie algebra of all meromorphic vector fields to the product of these Virasoro algebras related to these different punctures. I have a name for them. And then this guy acts here. So this means that those meromorphic vector fields act on this infinite dimensional vector space, and I take co-invariance. I consider equivalent to 0 all vectors which are obtained by action of this Lie algebra. Okay?
But you don't have central charge, right?
I have central charge. Central charge is there. I'm just not talking about this.
How you determine?
Huh?
How you do you determine it?
It's generic.
No, I start with representations of the. So first of all, the central charge is there from the beginning. So from the beginning, I say I have some kind of central charge I'm talking about. It's from there. Then I say I take representations, this Fermat models, representations of Virasoro algebra with a given central charge. And this central charge is there from the very beginning. It's probably should. It's a very important player here. The central charge. C. It comes as an eigenvalue of the center of the Virasoro algebra, how it acts on my Fermat model. It comes in the construction. And so this is part of the data on the left. And now it's clearly, thanks to Renat's question, so it's clearly, you see that it depends on the complex structure on the surface. Okay? Are there any other questions? Yes?
So C sub sigma is supposed to be constructed from the, from there, from that in the box?
Well, who knows how it's supposed to be constructed? So I'm going to explain what one may hope for and what actually might be possible to hope for, and then you'll see what kind of object this is. But this is the main player. So I would call it conformal block. This is misleading to many of you because, like in the previous lecture, this word was using in a different context. You call the space of this covariance dual this, you rather call conformal blocks. But there's some kind of distinguished vector which is supposed to be here. And so my goal is to explain why it should be here and how it relates to the previous story. And this whole relation is kind of, the main point of the story is to make this work. Okay.
So the modules, you assume Verma module, or is the quotient is also fine?
No. So I'm talking about Verma models,
Okay.
for example. So there is a ramification of the story. So sometimes there is a kind of version of the story which relates to, rather than SLN, like to SUN, you're talking about Vezzo-Minovitn theory. And in this case, you take something smaller than Verma models. And in this case, the story becomes very manageable because those spaces become finite dimensional, and they come with connection, and people understand this, I would say, very well what's going on. But this is a case where it doesn't happen. So we have the story which is kind of infinite, it takes to infinite dimension. The spaces, those spaces are infinite dimension. Okay?
Do you expect when you move the complex structure to span the C sigma span the whole Hilbert space or not?
This I don't know. I don't know why I should expect this, probably not. But I don't make any claims about this. Yeah.
So here you don't have the affine algebra also acting. So here you have these meromorphic vector fields, but you don't look at the action of the affine algebra.
There is no affine algebra here. So I'm talking about, in the case of SL2, I'm talking about action of the Virasoro algebra.
It's only SL2 here.
So in the case of SL3 or SLN, you are supposed to talk about higher analogs of Virasoro algebras, which are called W algebras. Your question is, they're supposed to be here, Kazmudi algebras, where they are. Yes, they are here, and this Virasoro algebra obtained by some process which is called semi-infinite reduction or the infinite Sokolov reduction or something like that. But today I'm not even going to touch this. if you want to define what is W algebra, we have to start from there. But I'm not doing this. Okay. Any more questions?
No,
Yeah.
sorry. So the C sigma, is it supposed to depend on the punctures and on their parameters?
C sigma depends on sigma, and absolutely great question. So I was about to put this. So first of all, here you clearly see that you have these parameters. And here I just start writing and said you don't see parameters here, but actually they are there. Thank you. There is this vector, and it's precisely the same data. Lambda 1 is on lambda n. And they live exactly in the same thing, you think, but actually they live in a dual thing. If you think about this, it's kind of, there's something is going on here which probably you don't want to hear. There's this Langland's duality. So it's not quite true that this G is the same as that G, so it's supposed to be Langland's dual, but if you don't want to hear about this, don't look at this. At this moment, it doesn't matter. And for GLN, there is a difference, but it's not that essential, so we can start talking about this. But so basically, I'm saying that up to this previous, this lambdas is the same as there. So my Hilbert spaces depend on some parameters. And that's exactly the parameters which you had in the left-hand side. And so definitely, these vectors are supposed to remember about these parameters. Okay? There's a family of vector spaces here and family of vector spaces here. So, any other questions?
Are these lambda going to be the monodromy?
No. Well, these lambdas are monodromies of this G-local system around the punches. Yes, the conjugate, the classes. But I'll say this later. Okay, so now what the statement is supposed to be? The statement is supposed to be like this, that there should be something like kind of question. Can we hope that you have the following story, that on the left-hand side, you have this co-invariance of the sigma WG, and that's a vector space. So the co-invariance of this and so on, lambda n. On the right-hand side, we have this vector space H, G, S, lambda. Can we hope that they actually isomorphic? What we definitely want to hope that this guy has the same size as that guy. For example, if this guy is just one-dimensional, that's supposed to be also one-dimensional. But can we hope that they're isomorphic? And if this would be the case, maybe we can hope that there is this vector I was talking about before, sitting here, highest weight vector. And maybe it corresponds to this vector, which is not exactly a vector sitting in this space, but so maybe we can hope they correspond to each other under this isomorphism. And the answer is that this cannot happen. No. There are statements in the literature that maybe, or maybe just people talking about that they're isomorphic. They absolutely cannot be isomorphic because this is something like Hilbert space. And this is some kind of space which has entirely different structure. So it has some distinguished vector, and then you have a descendants, and then descendants, and so on. It has a structure which you don't really see in Hilbert spaces. And for this or many other reasons, they cannot be, you cannot expect they are literally isomorphic. But, and that's what I'm going to explain later, there is something like that is going on.
You said that it was kind of obvious that they had the same. You said it was obvious that they had.
Not at all. Not at all. This is a big conjecture. They are of the same size.
So that is true.
It's not true. It's conjecture. Conjecture. They have the same size.
So for a physicist, it's true then.
Huh?
Then it's true for a physicist.
Well, I mean, it depends
For a
on
physicist.
It's true.
This conjecture, I know this conjecture is responsible for that. I don't know
provide some examples where this is true.
I don't think so. I mean, there are some arguments about this which convince you that this maybe is supposed to be true. But even if you take the simplest possible case, when you have CP1 with 3 points, and the group is SL3, it's quite a conjecture that it's supposed to be the same size. It tells you what the size of the covariance is, because what I didn't say, but what I'm going to say is that I'm going to describe the right-hand side in detail. And so the right-hand side is more or less under control, under complete control, more or less under control. The left-hand side, well, for some people also under control. The relation between them, that's the main point. So, for example, the fact that they should be of the same size, it's a conjecture, but okay. Okay? All right.
So, question. So you mentioned that space of covariance is infinite dimensional.
Yes.
So what does it mean, the size then?
What?
The size, what does it mean then?
Good question. Now let me formulate precisely what, and even if you talk about Hilbert space, what does it mean that it has some size? It could be finite dimensional or infinite dimensional. But it's infinite dimensional, what does it mean that it has size? So here is a more precise conjecture since Renata, so I'll try to formulate this more precisely. But it's not quite true that this is a whole data. There's much more to the data. And then after this I finish my kind of pushing down and start talking concrete things. But there is a Q deformation. This is all known. A Q deformation. Let's call OQ of this algebraic variety of the algebra of regular functions on this complex variety, which we call the space of flat connections. And then there is a somewhat better object, it's called the modular double. This is this algebra tensor with essentially the same thing, but for different Q, and not exactly for this G, but for Lagrange group G. Otherwise, it's the same. And so Q is exponent of I power H, and Q star, in the simplest case, is exponent of I pi divided by H. This is modular duality. And if it's not simplest, maybe you have 2H, or maybe you could do 3H, doesn't matter. So this is this gadget, so it's a tensor product of algebras. And so the main point is that this algebra acts in this sort of Hilbert space. I said it acts, but actually it acts by unbounded operators. So it's not clear. It's like saying that the operator e to x acting by multiplication to a function f of x. It's like saying that it acts on L2 of R. It does not, of course, because if you have function of L2 of R, if you multiply by exponent, it's not an L2 of R. But then you can talk about some domain where actually still an L2 of R. And something like that happens here. There is explicitly constructed, and that's the main point of this business, action of this algebra on this space, but then it comes with domains where it actually acts. There is some domain here called Schwarz space of this guy. And since there is a Schwarz space, there is a rule to this. And now the conjecture, so the main conjecture that there exists canonical non-degenerate pairing between the left-hand side and the right-hand side. So on the left-hand side, you start with a space of co-invariance sigma WG of this V lambdas. And on the right-hand side, you have the Schwarz space. So have the Schwarz space. And that's supposed to be non-degenerate pairing. And the point is that it's non-degenerate and continuous on this guy, on the Schwarz space. Schwarz space comes with Fouché topology induced by this algebra acting by unbounded operators. There's some construction of that. And so,
what does non-degenerate pairing mean?
Huh?
What does non-degenerate pairing mean?
so if you have two vector spaces and you have some kind of pairing, so you can ask, well, is it true that if you have a vector which is 0 for all other vectors, whose pairing with all other vectors is 0, this vector is 0. So if this is true, you call this non-degenerate pairing. Okay. So you have here quite complete vector space. This is a topological vector space here. And you have here vector space of entirely different nature. It's kind of space with a sort of almost basis. And it's kind of discrete. It's like space of polynomials. It's nothing like L2 of R. It's like space of polynomials. And then the conjecture that there's some kind of natural pairing between them, canonical. Non-degenerate in the sense that if you have a vector here which gives you 0 functional here, then this vector must be 0. Okay? And other way around. So if you have such a thing, I say, okay, then I declare these two vector spaces to be of the same size. That's a sort of definition of the same size. For example, it cannot be this is one dimensional, this is infinite dimensional. That's the not answer to your question. Is that okay? So in this sense, they are similar. But if you look at this, it's still very strange because this vector space has some data. There's action of the mapping class group here. And this space has no data like this whatsoever. The mapping class group does not act there. Again, I'm about to finish this kind of general part, but if you're talking about the Vladimir theory, actually you have this action there as well. Why? Because in this space, this is, maybe I should write this. So, what you have here, you have Morley space of genus G surface with n punctures, and you have this bundle of co-invariants here. It actually lives on a slightly bigger space, but for you, I'm not going to touch it. There's some C-star bundle of this, doesn't matter. But there's basically bundled here, and the fibers are infinite dimensional. But also there is a connection. And so if fibers are finite dimensional, then there is a monodromy representation. So the fundamental group of this MGM will act on the fiber. And then the fiber is supposed to be paired with this space SG, and then there is a mapping class group acting here, and then the pairing is supposed to be equivalent with respect to this pairing. But unfortunately, this is the case in the Vladimir story. This absolutely cannot be the case in this story, in Liouville's story, because there is a connection, but this connection is not integrable in a very brutal sense. So you cannot hope to parallel transport things here, and so you cannot hope to have the action of the mapping class group. Nevertheless, this is not a contradiction. And I will try to explain at the end why this is not a contradiction. How this action appears without making contradiction with its total absence on the left. Okay? Yeah?
Are you saying that if you have an action like a transformation given by a consultational formula, so we have an action by a group given by some integrals, like it is some operator acting on the infinite dimensional space, and the kernel is known more or less explicitly. So
which space are you talking about? Right hand side or left hand side?
Left hand side, the space of
No.
blocks.
No. So there's no action.
But do you prohibit this action by operators on the infinite dimensional space, or
there is no action? This means that if I think about this pairing and I make a loop and come back, I'm supposed to get precisely this pairing again. No action on the left.
but then what did Poisson National compute?
It's not my business. No. So I will explain in the end how this is possible, but to make sense out of this, I need to give a construction of the right-hand side. Without that, it's a little meaningless. I already went too far, like talking about two general things. So that's the end of the general picture. So
What was the role of the modular double in the Schwarz space?
First of all, it exists.
Mm-hmm.
And it makes the story rigid. Without double, all this breaks down.
Okay.
So it's the idea of Ludwig Fadeev originally, so it exists. It takes here, and it is very essential because without this, all the definitions would not make too much sense.
So you define the space S using the modular double?
Definitely.
Yes.
So the problem with that, so if I just restrict to this, there's a huge algebra, this one, which commutes with that. And whatever statement you make, like there exists natural isomorphism. In what sense natural? Because you have this guys which commutes with everything. You cannot say that there are two spaces identified in any sense natural way. It's not rigid because you can use by the other operators. That's the main point. But if you add it, then it fixes the freedom. Okay? So what I'm going to do, I'm not going to talk at all about the left-hand side, maybe till the end, but I'm going to go through the construction of the right-hand side. And I'm going to explain how this, since I constructed, this is much more, yes, just a second.
I'm very sorry, but...
Just a second. So I'm going to explain this, and there's a general machine, this quantization which does this, assuming that you have some kind of, you find some structure on this space of flat connections, like some coordinates. Yes?
Sorry, but you said that this bundle of co-invariant is infinite dimensional.
Yes.
And then you said it is finite dimensional.
In some relative of the story, which is called the Zumino-Witten story, when the group not SL and R, but like SUN, there is a similar story. And in this case, everything is finite dimensional. And all this makes sense without this Hilbert space, Schwarz space, all this stuff, not needed. And then there is a statement that you can describe the monodromy of this flat connection in some terms.
Thank you.
Mm-hmm. All right, so now I'm going to talk about the right-hand side. Any more questions before I move there? Yes?
Maybe one question for the left-hand side. So for the SL2 case, I can understand to define the co-invariant, you can use some homomorphic vector field to generate some
Yes.
PSR algebra.
Yes.
For general W algebra, how you generate what?
There is a machine. There's a machine which does this. The spiral algebra. So I mean, you can do this in more elementary ways, but there is a machine which exists now in algebraic geometry which does it all the way through. So I'm not talking about this. It's called chiral algebras business like. It is high end of the story, so you don't need to go there. But if you know there, listen to people how you do this. Dennis and Greenfield approach to vertex algebra, spiral algebras, and so on. So there is some way to do this. What I'm saying, you can do this in a kind of in more physical terms, talking about this tensors analog of stress energy and tensor. That's exactly what Bernard was. Bertrand was talking about this TW and so on. You can express this as this term.
Yeah, but this is for the SL2 case.
For SLN case or for any group G case.
Okay.
This is known, but this is completely beyond the radar of the assumptions. So again, the technique is known for this. It's either do this in physical terms for GLN, or you do this in terms of chiral algebras by Vincent Winkler for any group G. But you can do this. Okay. All right. So there is one more thing, is that if you want to talk if you think about string theory, still on the left-hand side, not about this side, then this is just Liouville's theory is just a kind of intermediate step. And at the end of the day, you want to get something, this conformal blocks, which lives in the moduli space MGN. You're going to take the lengths and you're going to integrate this over moduli space MGN. This raises the questions, what are you going to do if your surface has holes like that? And so I'm just saying there is an answer what you're going to do in this case today. I mean, we propose some answer, and if I have time, I will explain what you need to do, but it's not an obstacle. But now let me go to entirely different thing, to construction of the right-hand side. Okay? Any last time for questions before I raise left-hand side? Yes.
If we're looking at representations of pi 1,
Yes.
does that mean that we're only looking at primary fields?
Not really. I mean, we have the space of point variance, and if you would have parallel transport, and we don't.
That's on the left.
You don't have it. You have it as a monoidal story. Then you can parallel transport whatever you like, and you can ask the question what the monodromy is. But we don't have it.
One other question.
Yes.
So, is this about these SLN connections or about Liouville? Because there is a slight difference about this conformal constraint. If you have SL2, you have to also constrain it to get, you know, Liouville. If you view it as WZW, to get from the SL2 action, WZW action to the Liouville action.
Well, I'm not talking about WZW.
I know.
I'm not talking about Liouville action. I mean, I can, but it's not.
It's just SL2 or SLN.
Not SL2, any group G.
Any SL.
But there is an algebraic construction which tells you that in the realms of representation theory or algebra, if you start with a Riemann surface and you have representations of your Riemann models of some kind of algebra like Virasoro with generalizations, this is algebra, just algebra.
Right.
Then you can make space of coinvariance, and there was a question how you do this for SL3, and I said that there's a way to do this, but I'm not going to explain how. But there's algebraic construction which produces a vector space.
Okay.
And I'm saying that this algebraic construction is supposed to be paired with what I'm going to define now. This pair is supposed to be non-degenerate, and if it would exist, unfortunately I already raised this, if I would have this pairing, that's actually very essential. If I would have this pairing, when variance tensor Schwarz space to C, then I can take this vector. And then this vector will produce me some vector, let's maybe P. You can take P of this vector. And this belongs to the space of distributions, cluster distributions here. And this is the conformal block in my terminology. It's some vector which lives not in the Hilbert space but in the corresponding space of distribution, and this is somehow the most interesting part of the story. So in the previous lecture we have formula, DOZZ formula for this vector. In the case when you have so-called sphere and SL2, then this vector will be in one-dimensional space, and there's a formula for this vector in terms of lambda and so on and so forth. But in general, this vector lives in some infinite dimensional vector space, and you want to know what this vector is. But I emphasize that it does not live in the Hilbert space. At least it's not supposed to be living there. But that's how its definition is a consequence of this structure. All right.
Sorry, so what does the DOZZ formula have to do with conformal blocks?
DOZZ formula, it gives you 3-point correlation function. The 3-point correlation function, so if you're talking about conformal blocks, so this is a function, I mean, it depends if you're talking about function or absolute value square of this, or vector absolute value square of this vector. But if you're talking about SL2 case and 3 points, then the corresponding space of coinvariance is one-dimensional.
Right, but the conformal block is just product of powers of Z1 minus Zj, Zi minus Zj, right?
There's some kind of simple thing which we kind of suppress because conformance, but then there is some this beautiful formula in terms of this epsilon function and so on. It tells us that in this space there is some kind of distinguished vector up to the Zi and so on.
But then you are talking about correlation functions in Liouville theory,
yes,
aren't you?
Yes. This is correlation function in Liouville theory. Yes. Okay. So if I take the absolute value of this vector, which does not quite exist because it's not in L2 and so on, if you to address these problems, you would be able to make somehow its absolute value square. You're talking about correlation function. Yes, exactly. That's why it's the most. This is a correlation function. Yes. If this would be in a Hilbert space and the norm would exist, I would be talking about correlation function. Yes. And so for 3-point punctured spheres, this vector space, fortunately, one-dimensional. After you use conformal invariance to somehow see it one-dimensional. And this vector, and it's a Hilbert space which has length, and that's a correlation function. Yes. And this DOZZ formula is just for that vector. And so what I'm saying is that here you see more general objects, and as far as I understand, we know not that much about them. But at least I want to explain where do they live from the right-hand side, okay?
Is this conjecture justified by some examples, maybe? Is there evidence?
I made this conjecture now with Lin-Fishen about, 5 years ago, in attempt to formulate precisely what does it mean, the hope that somehow these two things should be related, although they're obviously not isomorphic. So, and then there is some evidence for that I can talk about, but it's very far from being proved. I firmly believe this is correct, but it's very far from being proved. But at least I start from this because it gives some guide. So why I'm going to talk about the right-hand side? Because that's where half of the story lives. And so I want to understand where it lives to be able to construct some vectors. And maybe the last question. So Renat asked, do you have any evidence? And maybe the question is, how do you know that in this Hilbert space there is a single vector? So this has justification as follows. So there is a Lagrangian of G opers. In the case of SL2, I'm talking about just equation dz squared plus quadratic differential, which just lives in the space of these flat connections in the complex group on this topological surface. And so this Lagrangian of G opers is Lagrangian for some symplectic structures there, but it depends on sigma crucially. And so if you quantize this, the general yoga of quantum whatever means that if you have symplectic space, it produces a quantization, some vector space, and you have Lagrangians, it produce a vector or vector up to scalar. So if you quantize this, you get this C, I forgot what the name I use for this. You get this conformal one. C sigma. So this vector is supposed to correspond to quantization of this Lagrangian. But we don't know how to do this. And this is very non-trivial because this space has some algebraic structure. So you know what the algebraic functions, regular functions here. But this Lagrangian of focus is defined in a way which looks transcendental from the point of view of that algebraic structure. So there is Riemann-Hilbert correspondence going on. And so even if you knew how to quantize Lagrangian, still it's some transcendental correspondence. So it's not clear why it should be quantized and so on, but that's the picture. Okay? All right, let's do the quantization. So these are flat connections. So it turns out that in order to do quantization in general, there is some kind of combinatorial gadget which appears, which surprisingly seems to play a major role in many different contexts. So it turns out that there is something which I called ideal AM or GLM bipolar class. On this S. And so I'm going to give you an example. So let's suppose that my S, this is not the case which I consider, but let's suppose it's just a triangle. I consider surface with punctures, but that's a triangle. And let's suppose that I give myself some M, So I'm going to construct some picture, some bipartite graph. I'm doing this as follows. So I take some subdivision this is going to be the case when n equals 4. So I draw these parallel lines here. Here. Not exactly straight. Here. And then this is just a cartoon, and then to get the graph, so I take here some white or red points. And then in between there are points of the other color. Let's call them blue points. They are centers, so there are triangles which look up and the triangles which look down. So up triangles, small triangles which look up, their centers are red points, and small triangles which look down, their triangles are these blue points. And then I connect them into a graph. And that's my object. So I got a graph, which I call graph gamma 4. It's related to triangle and m equals 4. And so in general, so I consider some bipartite graphs. So what is a bipartite graph? Once again, so now I move to more combinatorial things, so you can forget whatever we discussed there. So if you have any questions, you're supposed to ask me.
So where do the edges in the boundary go? Where do the edges in the boundary go?
So the edges are blue. Yeah. This is not the edges. This is
no, but the ones that exit your big triangle.
Huh?
Where do the half blue edges on the side?
Where the blue edges go?
Yeah.
Good question. What if you decide to do something more complicated? So when you have a surface, so let's suppose you have a torus. So torus means that you take a square and you glue the sides of the square. We can triangulate this in two triangles. And then I can take this picture and I can glue. I have two triangles which I'm supposed to glue. Then if I have the second triangle, I have exactly a picture like that. Okay? And then I just continue this naturally. So this goes like that. Hope I made this. Right. And then I can keep going. Well, then you're going to see here again, this looks like a little scandal because that's not what I should see, but at least inside it's okay. And then you have it here. And then you see a similar picture. The only little issue is that it seems to be this not a bipartite graph because they want to be related by, but they need to be related like that. So in these spots, you just modify slightly this construction, and then you get the bipartite graph which will appear on the torus. But you get it just by amalgamating these two pictures on the triangle. And then if you glue the torus from this thing, you see that you have this rank 4 graph on the torus, and you can do this on any surface. So this gives you construction of something, some bipartite graph on the torus. Now, what is the property of this bipartite graph? There is a notion of zigzag passes.
It was not important to start with the triangulation, right?
Sorry, what?
You could have started with any bipartite graph on the
surface. So in a few minutes I'm going to say how this looks without triangulation, but this is just a motivation to introduce some definition. I'm saying that I produce you an example of something, and then I'm going to explain what are the properties of this something and how all other something looks like. So to do this, I have to say that there is a notion zigzag passes. Whenever I have a bipartite graph, so it goes like that. So you have, so you can go, you turn left here and right here and left here and right here, and you have a zigzag pass, okay? Because here it goes somehow. Maybe something more complicated. Who knows? But that's how the story looks like here. So lots of something here, but then there is a zigzag path which turns left at blue and right at white. And so let's draw it here. It looks as follows. Go like that. And the next one goes like that. Okay, so and then I can go like that. And maybe I can even go like that if I want. So you see that you have this green zigzag passes, and they obviously like, so if you imagine that your notorious that they make all the way through, and if you imagine this is like a big tessellation on triangles of your surface, and you make these pictures, and then you consider these green passes, they all go around the punctures. That's a property of this construction. And if you do this, if you think about this, then you notice that there are exactly 4 or 3, it depends how you count. There's the number of these green circles around every punch is the same. Okay? And so now I schematize this. I say, let's consider on the surface bipartite graph, which has this property that if you consider the corresponding zigzag passes, so that's the definition. So a bipartite graph gamma on surface S with punctures is an AM graph. AM refers to PGLM or GLM. If the following is true, the part of the surface to the right of each strand is a disk. For example, in this case, you clearly see that you have a disk. Like, if you have a complicated surface, these green passes are going to go like that. They're going to make a circles. And each of these zigzags, it bounds inside a disk. That's the topological property of this. So that's the first condition. And then there is some technical condition, which you really shouldn't ignore. I don't want to talk about this. So basically, if you have this condition, so this is the graphs which are suitable, and then the main result is that this graph is supposed to produce you some explicit chart on this moduli space. Yes?
What do you mean by strand? Is it a closed zigzag?
So, okay, you have a bipartite graph. Bipartite graph is something which lives on a surface. Oh, sorry, on the graph. But this graph is a ribbon graph, so it lives on the surface. So I can push slightly this bipartite graph out of the graph to make it live on the surface, to make it more visible. And so these green guys, I call them strands.
Okay, that was my question.
Oh, sorry, okay. All right. Now, why this works for us? Because there are some elementary modifications.
So m refers to an integer here.
Sorry.
Little m refers to an integer here.
Yes.
And but in the definition.
Excellent. Thank you very much. I was hoping somebody asked me this question. So in this definition, you see no m like that, but I'm saying that it's automatic, and there is something related to this picture which I'll explain right now, since you asked. And this something is a spectral cover. So I claim that if you just start with this graph, with this data, you produce a bigger surface, combinatorial, which comes with canonical projections to your surface. And this bigger surface comes with degree of this map, and this degree is supposed to be m. So this m, any graph like that, is have intrinsic number integer built into this definition, and that m refers to this m, but I didn't define it. So let's talk about this rather than about elementary transformations. So spectral cover. So the spectral covers are supposed to be something which is called the spectral surface, which you build from gamma, and will come with projection to your surface S. So this is called spectral surface. The name is legitimate, so if you hear talk number 1 today, it's related, but you don't see this immediately. So how we build this? So if you look at each puncture, then you see that it produces some disks. And these disks are sitting inside each other. So this dp1 inside this dp2, and so on dp, some number. It will be m in the end, but so far we don't know. What is this? So this is dp1. So now if you look at this disk, that's my dp2. And if you took that one more disk like that, that's going to be my dp3. So because we have family of concentric circles, we have family of concentric disks which go around each puncture. Now we are going to do the following. So at this surface, these disks, they sit on this surface. But now I'm going to take each of the zigzag, cut out this disk, and put it into the storage room. So I put in the storage room the small disk. Then I put in the storage room a bigger disk, which contains this one. I don't pretend I took it out. Second is the third disk, and so on. So for every puncture, I have some storage room where I have collection of disks, bigger, small, bigger, and bigger, and so on. For puncture P, for puncture P prime, you have small, big, and bigger. And now I'm going to glue all those disks as follows. So what you note is that if you have an edge or bipartite graph, then there are exactly two zigzag passes which pass through this edge. So there is a zigzag pass which comes like that, and there's one which passes like that. Okay? They are precisely, I draw them close because they go along this edge. You can call this edge E. And so for whatever edge, there are exactly two zigzag passes, and one of them defines you a disk which is on the right of it, and the other defines you another disk which also on the right but of this one. So this means that you created two disks, for example, this one and this one. And by construction, these disks come with a unique edge here and here, which is common edge for those disks. That's precisely this edge. So this means that I can take this disk from storage room and this disk from storage room, and I can glue them together like that. And then I get, I glue two disks, and then I glue all disks together, because for whatever disk it has sides, which are edges of my graph, I take one of the sides, and I found for this side the other disk, which borders the side, and I glue them together along this edge. And by construction, I will get a surface such that every edge of my original graph will be edge of some pair of disks glued together. So I claim that after this I constructed some topological surface. Is that clear, or somehow I need some comment? Any questions about this? So this surface is the spectral surface. Is that clear? Yeah.
Can you describe the projection?
In a second. I got abstract surface which is built from disks which we are taken from storage room. Okay? Any questions about this?
So for it to be a spectral surface, you also need to embed it into some...
Not embed, but project it, and that was the previous question. Spectral surface is a surface which projects down to your surface.
It does not need to be embedded into some total space. So
No. Just abstract surface. It's not embedded to cotangent band or something a priori. It does, but we are not talking about this at the moment. It does, but wait a second. Now, what is the projection? So this surface is built. Answer your question.
Just one before before you go. So both disks will correspond to different punctures.
Probably, yeah. Yes, definitely, I would say. Yeah. Okay. I mean, it could happen that it's actually a good question because it could happen that your surface has just one puncture. And so then you better go to little cover of this and do that and project down. So there is little things like this you can do, but not just assume the course is sufficiently big and you don't run in those little travels. So then it corresponds to different punctures. You better do this on the universal cover than project it down, that's what I'm saying. Now, so each of these disks from the storage room was taken from the surface, so it projects down to the surface automatically. Therefore, this surface which I constructed is automatically projected down. So this projection is automatic. So I get this cover, okay? Yeah.
So this spectral surface, does it depend on Pn, on lambda, on the central charge?
It does not. It's a topological gadget. It lives on the right-hand side. I have a left-hand side and the right-hand side. Left-hand side is complex geometry. Right-hand side is topology. But topology remembers by these lambdas, and they do not enter to this construction. It's just topological construction which allows me to construct some coordinates on the space of flat connections of PGLM flat connections. Then I can talk about the monodromies, take eigenvalues, and I get your lambdas. But not yet. Okay?
So this M is arbitrary? You just take...
No. You get a cover, and this cover has, as any topological cover, it has some degree. So M is degree of cover map. It's either degree or -1. It depends on some conventions. I'm not going to discuss this. But it's basically the degree of the cover map. In particular, you see that around every puncture, you have the same number of zigzag loops, which is not obvious from the definition. Okay? All right?
So is there any requirement on where the punctures are? I mean,
what?
So the faces of this bipartite map, should they contain a puncture, or can I just put the puncture anywhere?
No. I mean, this original surface has punctures, so this disk, they also have punctures inside.
Yes.
So this spectral surface, it also has punctures.
It need not have punctures.
No, it has punctures by construction, and all those punctures project to the original puncture of the original surface.
Sorry, where are the punctures in the picture?
If you have a disk, this one, it has a puncture here.
Yes.
So when you put it in storage room, you remember that you had a puncture.
So it's like a torus, you have a puncture.
Yeah.
And you open it,
So this is a one puncture torus here, or it's many punctures?
So whatever you take, any zigzag path, it goes around one Yale, in this case, puncture.
Yes, so this is a one puncture.
Every zigzag path, there is unique puncture.
Is there
By definition. Or by this construction or by definition. But let me... Is that okay? So here is the main statement about all this story, which explained why I was talking about this.
So you cannot handle unpunctured surface. You can't handle unpunctured torus.
No. This way I cannot. And actually, this whole story, handling something without punctures, is a big problem, a big pain. No, definitely not. Okay. So the main theorem is the following. So let's consider the moduli space. I call this EGLM. Yes. So the parameterized data by L and the framing beta P. And so this L is a PGLM flat connection on S. And this beta P a choice of an invariant flag, of a flag invariant under monodromy around P. So, for example, if you have a two-dimensional surface, and as Renat pointed out, I must have some branches. But if it's two-dimensional, like it's the case of PGL2 or SL2, then you have two-dimensional bundle here, and I say that if I go around this puncture, I'm supposed to have a flag. So what is a flag? Flag means that you have a vector space, and then you have called F0, and then has for dimension 1 subspace, for dimension 2 subspace, and so on. And for dimension m subspace is going to be 0. So you have a sequence of subspaces, but in this case it's just one-dimensional subspace. So there is this one-dimensional subspace such that if you go around, it stays invariant under monodromy. This does not look like a big deal because generically monodromy is given by a matrix with two different eigenvalues, and just take one of the eigenvalues and take this eigenvalue. That's the Sextor data. So it looks like a finite data at every point, and n factorial choices. And then there's a theorem about this. So if I take this space, but not the one I was talking about, flat connections, theorem, take any graph and a bipartite graph on the surface S, then there exists canonical open embedding of the following thing. So you take this graph, let's have a name for this graph gamma. Then you take the space of rank 1 flat connections on this graph gamma. And this is something very clear because this is just one-dimensional cohomology of this graph with coefficients in C star. So it's basically isomorphic to C star as to the number of loops on this graph. So it's very, very clear thing with canonical decomposition of product of C stars corresponding to loops, to faces. So this embeds canonically to the space X PGLMS. So this means that this is an open embedding. This means that almost every flat connection with a flag can be uniquely presented by a one-dimensional flat connection, like one flat connection on this graph. And so this, a little later, this will provide the quantization because this space is very easy to quantize, Q-deform quantize, whatever. And so the quantization will consist of quantization of these spaces, where it's just extremely easy to do. And then we have many of them related to different graphs, and the claim is that they all sit together in a coherent way and produce, in the end of the day, the quantization I was looking for, the Q deformation. And they also will produce this Hilbert space, but this will be in the second lecture. But so far the combinatorial part is over, so if you have this AM graph, for example, something like that, I introduce some coordinates on an open part of my space. Okay? So who are those coordinates? They're just monodromies of my flat connections along this faces of this graph. So
I think it's time. Huh? It's time.
It's time. Then that's it.
Let's thank Alexander. So we have maybe 1 or 2 minutes for additional questions. We already have a lot.
Yeah.
log m?
What?
Why log 1 and not log m?
But that's the whole point. So you want to study moduli space of n-dimensional flat connections. And it's a complicated space. And I want to say that generically you can present them as rank 1 connections on some different space, which basically is a speckle curve.
Okay.
And as soon as you did this, you get coordinates for the original space, and you get quantization of this chart of the original space. And just using the Heisenberg representation, you get this Hilbert space, operator settings there. So all these gadgets I was talking about in the beginning, on this particular charts are given to you after this. But it's not canonical because you cannot choose one bipartite graph which does the job, because if you have symmetry like action of the making class, you're going to get a different graph. So there is still something to do. Okay?
Maybe in the gluing, I was a bit lost because you pick some edge and then you do the gluing.
Yes.
But then, how do you get the whole surface, and how does the degree
Okay.
rise?
So I start with the original surface on which I have lots of disks. Now I said the story about the storage room. I take each of these disks, take its kind of copy, and put it in a storage room. Then take a bigger disk, take its copy, and put it in a storage room. So now I have much more disks than I had before, and they're all kind of independent. Now I'm saying that if you take any edge of this graph, then there are exactly two disks from this set which stick naturally on this edge, but not anywhere else by construction. So I glue them together. And so now I take all these disks from the storage room and I glue them by the rules to the edges.
You take all edges and glue at all edges.
Yes, I take every edge and glue them.
Yes, okay.
The claim is that after that I get a smooth surface, number one. Secondly, this surface by definition maps to my surface. Finally, this map is unramified everywhere except black points. It's easy to see. And then it has some degree as map of surface to surface, and that's exactly it.
Particularly, you also get a graph on your new surface, right?
Yes.
So
Yes.
how is it related to?
It's the same graph. The graph
Example
will
back
change,
on that, yeah.
So this graph, which I draw here, is homotopy equivalent to the surface which I. This is why you get flat connections, rank 1 flat connection on this graph, or what is the same on the speckle surface.
Maybe one last question. Rafael?
Sorry to make you repeat.
Well, source of all questions. Okay.
So for every edge,
Yes.
you take the zigzags across,
Yes.
and you glue the corresponding disks.
Yes.
So the edges are naturally already in the new surface.
Yes. So I remind you that we wanted to relate when varieties organizational systems. So we start with a space called LGS, and which is a space of all G1 on surface S, normal isomorphisms. And S is a topological surface. Now, what is going to quantize? So we said that we want to quantize some Hilbert space and have some unit reaction of the mapping class group on this Hilbert space. So this is a Hilbert space. Well, if you want to do this, so maybe it's not a bad idea to consider the simplest possible case where we can do this, especially since this is not all the data. Remember that I wanted to have some subspace here, like cluster Schwarz space. And so how this looks in the simplest example? So the simplest example is when S actually is just a torus. In this case, the mapping class group is, you can say this PSL to Z. And so you want to construct this data. So this Hilbert space is going to be L2 of R. And if I just want to construct the action of this group PSL2Z on this Hilbert space L2 of R, so it acts, and this well-known construction is called Weyl representation. Actually, Weyl representation is the biggest thing. It's PSL2 of R, but we can consider some group Z. Weyl or Siegel shell Weyl representation. But let me remind.
Sorry, isn't SL2Z? Why P?
Z. So
no. Why P? It
well,
should be SL2.
This is so. If you want to construct Weyl representation, I will do something different. I will even put a central extension, but in this case, not going. I wanted to. Let me start with SL2Z. Okay. Well, I can just write formulas that there are two matrices like that, and they generate the group we wanted, and so I just need to write down some operator which acts there, and these operators are given by kernels. Minus x squared divided by and this one is going to be something like 1 over 2 pi I. But that's true, but it's a little enigmatic, and this is not the whole structure. So the whole structure is more. So one can check that this is unitary representation, but it does not. You have to start with some algebra. So it's going to be quantum torus algebra. And this algebra is going to act by the following operators. So you consider operator x1, which is translation by 2 pi I beta. That is some number. And x2, which is translation, not translation, a multiplication by the function exponent of beta t. And these operators act on the space L2 of R, but you immediately object that they do not act, but because this is multiplication by exponent and this is translation to the imaginary direction, so beta is some number. So this seems to be ill-defined. But then if this would be well-defined, then you can check that they formally compute the way they should commute. But this not the end of the story, because it turns out that there's another algebra which commute with this one. Let's call this y1 and y2, and they satisfy similar relations. And those operators, so they still act here, and they're given by similar formulas, where you have y1 is obtained by translation divided by beta, and y2 is exponentiation of t divided by beta. And then you can check that this algebra commutes with this algebra, and none of them acts, but you can define a so-called Schwarz subspace, which is a common domain of definition of that so-called Schwarz subspace. That's the simple Schwarz subspace I'm talking about here. And then they both is going to act there. And the point is that this group I'm talking about here, SL2Z, this acts by automorphisms of either this quantum torus or that quantum torus. I have to tell you how Q is related to and Q check to this beta, I pi beta and I pi divided by beta. Let's remember. So the point is that this group SL2Z acts by automorphism of these algebras, and so it's supposed to act in representation. But after I defined this action of the quantum torus algebra, this completely rigidifies the story. So I can just write down different equations for those operations, solve them, and then I will see that up to maybe scalar, I'm going to get representation of group SL2Z. So I don't have to, if I don't care about the, if I don't care about this, then I'll see that I get this representation which I wrote before. So this is the simplest possible example of quantization. As I said, this is basically, besides this yellow part, this is under Veil. And that's how we quantize the torus. So if you have another surface, like a compact surface genus G, and consider the group G, which is C star, the story will be exactly the same. So,
if you want only this representation, so PSL2 was the correct initialization.
so
If you want only this representation, PSL2 was the correct initialization. You had PSL2 at the beginning, then it was
there's the group SL2Z acts, and so we can investigate how -1 acts. It doesn't matter. Okay? So what I'm saying is that we can do the same for the group GL1, and then we'll get the same story will give me quantization of C star flat connections there, and this again under Veil construction of representation. Now, if I want to do for any other group G, I wanted to do something similar. So I wanted to find some coordinates which identify this moduli space which I'm talking about. I want to say that I can find some coordinates such that this is isomorphic with C star raised to some big power n. And then hopefully I found some information on this, hopefully it's Poisson space, and then I'll do the same. Unfortunately, this doesn't work in any other example, so this breaks down. Why it breaks down? Because this local charge essentially never existed, cannot exist, because from the point of view, let's say, of algebraic geometry, this space is usually not rational. This means that you cannot find open part of the space which can be identified with open part in some C star to n. So that's impossible. So what to do? The first thing we want to do then, we want to replace this space to a different one. This is the one I was talking about last time. We introduce space XGS. And I remind you that this is space of, so G at this particular moment is going to be PGLM. This will be flat G bounds on S. S has punctures now, it will be essential, plus an invariant, a choice of an invariant flag F near each punch. Now, what this space has to do with that one? So if you forget this data, so the data means that you have some flat connection, and then you have this flags framing. So if you just assign to this the corresponding flat connection, then I got projection to the space of flat connections. And generically, this projection is going to be n factorial to 1, n factorial raised to the number of punctures on S to 1. So it's generically it's a finite cover. So it turns out that this space, unlike this one, so the space XGS has rational coordinate systems and in abundance. And so I'm going just to construct them. And as soon as I will construct them, I would be tempted to continue this construction of the Veil representation. So let's do this. By the way, so I hope it's clear why it's n factorial to the number of punches, because whenever you have any point on the surface, there is a local monodromy, and it's just matrix, and this matrix has eigenlines, and the choice of the flag is ordering of these eigenlines. So if eigenvalues are different, then we have different eigenlines, and we have to order of them, and there is n factorial choices for that. So that's why this is n factorial to 1, n factorial raised to the number of punches.
M factorial. M factorial.
Well, thank you very much. So this means that's excellent. M factorial, yes. All right. Now, how to define coordinates? So basically, I spent the previous lecture trying to explain this. So now I'm not going to repeat this, but just do some crucial step. So to do the crucial step, I'm going to solve the following problem. So first of all, I'm going to change at this moment PGLM just to GLM, just to show how it works in slightly different situation. It doesn't really that much matter. And so I'm going to prove the following theorem. So I consider configurations of triples of generic flags in m-dimensional vector space. I can even say in Cm. Now the word configuration means that this is by definition triples of flags A, B, C. And these dots means that they have the same infiltration. So it's have like a vector space Cm. This is my A upper 0, then has A upper 1, and so on, and finally A upper M is just 0, and each of them is codimension 1, 2, 3, and so on. And so this is the data of the flag A dot, and similar to the other flag. So that's what means flag. Now, what does it mean generic flag? Before I say this, I'll formulate a theorem. So the theorem is that this is canonical one-to-one correspondence with a space of all flat line bundles on the graph. And this graph, I need to draw this graph. So I take such a picture, and I draw lines like that. And then I get a graph by putting red circles here and blue circles here. And so I get a graph like that. So this is a situation where m equals 3. And this is GL3. So this is GL3. Let's see, I was... Well, it's actually probably SL3. So I'll have to draw a big graph. So please forgive me, so I'll correct this. So there is some kind of graph gamma m. It is either GL3 or SL3, and I'll tell you which graph a little later. But so the statement is that if you consider configuration of generic flags in CM, you're talking about the case of GLM. This is the same of flat line bundles on a graph like that. And if you consider SL3, the graph will be slightly changed, but it doesn't make too much difference. So this is a one-to-one correspondence. Now, what is generic? Generic means that if you consider these three flags, and if you have any numbers A, B, and C such that A plus B plus C equal to M, then you can consider map from your vector space Cm to this Cm modulo A sub A plus Cm modulo A B sub B plus Cm modulo C sub C. And this map is obvious, you just take the quotients, and the condition is that this map is isomorphism. If it is isomorphism, and generically it is isomorphism, because it's generic. And so the theorem is that this is one-to-one. Now, how to construct such a flat bundle? So the game is that I start with three flags, and I want to construct flat bundle. Notice that there is no local systems, flat connections on the left whatsoever. Okay. So, okay, so I noticed that there is this vertices of two kinds. There is this circle, red circle vertices, and they correspond precisely to the collection of numbers A, B, C, which are non-negative integers, such that A plus B plus C equals to M minus 1. Is that true? I mean, tell me if it's not true. Then, if I consider another kind of vertices, which I call blue vertices, this is the same as similar connections of numbers A, B, C, such that A plus B plus C equals M minus 2. I might make some mistake, but I hope I don't make this mistake. It's like 1, 0. like 1, 0, 0, 0, 1, 0, 0, 0, 1. So we have 3 blue vertices and 6 those kind of vertices. And then the construction is the following. I take the plane. So the plane is going to be the plane ABC. So what is this plane? So this plane is this PABC. It just means that I take intersection of AA, BB, and CC. And because the sum of them, if they in blue, is 2 dimension 2, so this is 2 dimension plane, so it's a P-plane. And on the other hand, I can introduce a similar quotients, which I denote by L A B plus 1 C, L A plus 1 B C, and L A B C plus 1. So I start with this ABC, which sum to m minus 2, and so I add 1, so they now sum to m minus 1, so they correspond to red. And then I claim that there are arrows like that, which is obvious from this construction. There are 3 arrows like that. So why they're obvious, we'll see in a second, but if you believe me, then you immediately see that we are close to getting a connection, because, okay, I still have to get the connection, so I need to explain how to put, what kind of vector spaces to put here and how to put arrows. So one of those vector spaces, the L vector spaces, that's what you see here already. So the blue vector spaces are not yet there. So that is
the Sorry?
Yes?
Can you just remind me what L?
L is a line. I can't remind you because I didn't tell you. Do you understand what it is? Because,
Okay, remember. It's because I assumed that I missed it. But
no, I'm just checking where we are. So if you have these questions that you're following, this way. Otherwise, you have to stop. So, okay, so who is L? So L, and let's call this, I don't know, X, Y, Z, is what you think there is AX intersect BY intersect CZ. Same kind of intersection, but with numbers which you see as indices, okay? And since we have one more, this is line, and this is a plane. So we have this picture, but we also have a picture like that. So we can introduce another line, and I'm about to finish all this explicitly.
But red ABC is not the same as blue ABC. Is that true?
My ABC are the same here and here.
The arrows are
But then they sum up differently.
Well, this is true. You're right. You're right, yes. Okay? But those ABC are, I start with this ABC, which sum to 2, and then I add 1 to them, so I get the another indices. And what I'm saying is that the crucial part is that I have to introduce this space L. So I would call this L circle. And this is going to be L. Dot ABC is the same thing. So this is going to be the kernel of the map from L dot A plus 1 BC plus L dot A B plus 1 C plus L A B C plus 1 mapped to this plane PABC. Now, I'm not telling you how to construct these maps, but I'm claiming that if you look at those definitions, it should be obvious for you that this arrow exists and that arrow exists. And so this defines for me the space LABC. And after that, I just say that I have finally so I have this LABC. dot, and this maps isomorphically to the previous, which was L circle A B plus C, maps isomorphically to L dot A B C plus 1, and maps isomorphically to L A plus 1 B and C. So I claim that it's obvious from the construction and the definition what is generic that there are first of all natural maps, and these maps are isomorphism, not surprising because this is all lines. And that's precisely my local system, because it doesn't have a local system. This means that I have some vector spaces which are lines which live over the vertices of my graph. And that's precisely else with dots and with circles. And then I have maps between them. But I just did construct these maps. These arrows, I just constructed them. And so that's a local system. That's it. So I claim this is an isomorphism between the data given by the left-hand side and the right-hand side. Actually, it's very easy to construct the inverse map. So the proof of this fact is as obvious as construction. So, but it needs a little bit more preparation. So I look at this diagram, and I say, okay, let's suppose I have my flag A sitting here. So now I want to do the following. I want to start with a flat line bundle which lives on this graph, and I want to reconstruct 3 flags in 3-dimensional space. So how to do this? So I need to construct 3 flags. I'll construct one of them, which will be A flag. And I will do this as follows. So I'll say that we have a natural kind of filtration here. So we have some of the spaces below first grid, some spaces below the next grid, and so on. And what we can do, we can just introduce my vector space, usual vector space, by the following formula. So that's the V vector space, which corresponds to local system L, to flat. L is a flat line bundle here. As by definition, is going to be the following. So I take direct sum of fibers of L at the black points or blue points, map it to the direct sum of L at all points of other color. Maybe I call them red. But the what I do with this, I claim there is a map. This map is given by my connection. So I take the co-kernel of this. Okay. Again, so you have here 3 black lines and 6 red lines. So if you take co-kernel of this map, you get something 3-dimensional. That's your vector space. Now, why this vector space has a flag? Because it's just filtered. So if you consider everything which is below this green line, that's your vector space. If you do the same construction here, this means that you take sum of 3 reds, and then there is 1 blue which maps to them. Then the co-kernel will be 2-dimensional. And if you do it the last way you can do this, then it's going to be just 1-dimensional. And so you can check that that's the filtration in my vector space, which you get this way. If you do this for all other vertices, you get 3 other flags, and I claim these constructions by definition are mutually inverse to each other. Okay? So I prove the theorem if you don't mind. Is that clear? Is there any? Now, how do I use this theorem? So now I want to prove the other theorem. So if I have a surface S, well, I can consider any bipartite graph which I was considering before. I call this like AM graph, and I basically can run exactly the same construction. So I can say this is an exercise to write the same construction, and then it will provide me the line bundle by exactly the same kind of rules which lives on this graph. But I can do something less elegant. I can just say that I can triangulate my surface. And if I triangulate my surface, I do the same at each triangle. And then I have flags, like A flag here, B flag here, C flag here, D flag here, F flag here, and so on. And then I got my graph which is sitting here. And then the previous construction will give me a local system, flat connections inside of each of these triangles. And you check that by construction they're compatible. So this way I get flat connection on the corresponding graph in general. And so this proves that there is embedding of some torus C star to something as an open subset to the modular space of all these flat connections with flags. Because you can, if you start with a flat connection on this kind of graph, so you reconstruct the flags, and then you actually, you can argue that after this you actually reconstruct not just flags, but you reconstruct the whole flat connection. And so that's a nice example. So these are the cluster Poisson coordinates. Now, well, first of all, is it okay if I say that I prove the theorem that C star to something embeds as an open subset to modular space of m-dimensional flat connections with flags? Yeah? Is that okay, or you have questions?
So can I just make it sure I understood? So the number of flags will correspond to the number of punctures, right?
Flags sit over near the
punctures, and then and then we have the same amount of
zigzags which going around. Yes. And they're responsible for those for the reconstruction. When you do reconstruction map, you use the zigzags to produce the filtration to produce first of all the fiber at point near here, and then it comes with filtration. And this happens at every vertex. So reconstruction takes the line bundle in the graph and produces you lots of vector spaces near the vertices with filtrations, but then they're also related, they form a local system. They form a bundle connection also by construction. Okay?
So there's triples of flags, so you have 3.
Huh?
So why did you have a triple here?
Because I said I want to run this construction for very specific triples graph. This graph is what happens on triangle.
Okay, but then there's 3 flags, but you said number of flags has to do with number of singularities.
Yes, yes. So this is a good question because I didn't say this, but I should. That I now sort of consider this the surface which is not surface with punctures, but it's a surface is like polygon. And so this surface has vertices, which is this ones, and that's where my flag sits. Now, if I am going to build the big surface by doing this kind of triangulation, eventually all this data will build me flags near here and a flat connection on the whole thing. Okay? So I'm just saying, if you do this in a tutorial way, it's enough to do some triangle. Okay. Fine. Now, what does it give us? So, so we just prove a theorem, which I'm going to formulate again. Theorem. So any, let's call this S11 plus an AM graph on S, there exists canonical chart, canonical embedding of C star raised to some power n as open embedding of the space X PG LMS. So this has been proved right now, but now then the question is what happens if you consider different GLM graphs, and then there is this thing which is called 2 by 2 moves. So the situation is the following, that there is a way to connect bipartite graphs, well known to the people who think about this. You have a graph like that. You can change this to a graph like that. So the external vertices stay the same, but internal structure changes like that. Okay? So this is called so-called 2 by 2 move. And then there is a statement, it's a kind of theorem, that any two SLM graphs, or PGLM graphs, SLM graphs, can be related by a sequence of this 2 by 2 moves. I'm not going to prove this here, I'm just saying it's correct. and it's not that hard. I mean, it's possible to prove. After we have this, so if you want to understand how these charts are related to each other, there's only one thing to understand: how the charts are related to 2 by 2 moves are related to the other, to one to the other. And well, this can be done explicitly. But rather than doing so, I just want to explain the general scheme. So what we're doing now, we get the whole situation. So we have this graph gamma. Oops. It produces spectral surface, which was constructed last time. Sigma gamma. I will remind you what this is in a 3 different way in a second. And then this spectral surface produces lattice lambda, which is defined as first dimensional homology group of this graph with integral coefficients. Not this graph, actually this graph is true, but it's not what I want to say. Of this spectral surface with integral coefficients. And this spectral surface is homotopy equivalent to this graph. So you can say this is exactly the same as first dimensional group of this graph with integral coefficients. But the presence of the surface is better because it comes with the intersection pair. Okay? So just one graph we started from. It produces a lattice, produces some intersection pairing, but it also produces another part of the data. It produces a basis of this lattice lambda. So this basis corresponds to monodromies around the faces of this graph. Okay? And forgetting about the basis, but just the fact that you have this lattice intersection form immediately tells you that you can construct quantum torus algebra corresponding to this. So that's a very general construction. So if you have a lattice, I write it again, if you have a lattice lambda and you have some intersection form on this lattice with values, let's say in integers, then you assign to this some algebra which is generated by elements x lambda, and so lambda is element from your lattice. And these elements obey the rules that if you multiply x lambda times x mu, and don't forget to put here the coefficient q to my I'm going to write this in a bigger space. So I have a lattice lambda, and I have some bilinear form. It's Q-symmetric bilinear form, which is z-valued. Then I can introduce some algebra. I can call it algebra. It's quantum torus algebra. Relate to this lambda and the intersection form. So it's by definition, as a vector space, is just given by the elements x lambda. So it's span of these elements over Z, where lambda is any element of your lattice. And there's a multiplication rule that if you take x lambda and multiply it by x mu, then you're going to get x lambda plus mu. But it's not exactly the case because you have to put here q2 minus this bilinear form between the vectors lambda and mu. So here lambda and mu are elements from your lattice. And then you claim that this is, let's say, definition of the product. Then the algebra which has these generators corresponding to elements of the lattice and this relation where q is any complex number, this is a quantum torus algebra. And now I need to answer the question, what happens? So I said that if you start with a graph, you get the spectral surface give you lattice, give you intersection pairing. And now the question is how to describe what happens with all this data after 2 by 2 move. And it turns out that the simplest way to do this is to run more general definition and then to say that exactly the same thing happens in this definition. And so that's what I'm going to do right now, okay? So once again, attention please. So I said that I produce quantum torus algebra for every graph, and now I'm going to relate this quantum torus algebras for different graphs. I'm saying that rather than to do this explicitly, I'm going to present a more general setup where I can do this, and then apply this in particular case. All right? So that's a key point. So we want to introduce now seeds, the cluster seeds. So we start with generalization of this picture. We define what's a quiver. Quiver, it's a definition, is a data given by a lattice. Lattice means a finitely generated free abelian group. Then this lattice comes with a choice of a basis. A basis of this lattice. And it comes with an intersection point. So we call this data quiver as a Q. And as an example, if you have some graph as before, then it provides you the quiver given by lambda given to h1 of this graph with coefficients Vz, Ef given by the faces, corresponding to the faces of this graph And then the intersection form is from h1 of the spectral curve. Okay? So that's a quiver. So why it's called quiver? Because you can define a set which is a set of vertices. So these vertices are going to be like my basis vectors. Now, if I have two vertices, Ei and Ej, I connect them with three arrows if the scalar product, the symmetric product between Ei and Ej equals to +3. So that's the rule how I get the quiver. And vice versa, if I have a quiver-oriented quiver, I reconstruct lattice as a free abelian group generated by vertices and the skew-symmetric pairing which is compatible with this rule. Okay? So now I can say what is a mutation. So mutations. So given a basis vector, Ek, I'm going to introduce a mutation which takes my quiver Q, so quiver Q prime, which we say is obtained by doing mutation at the vector Ek. So how to do this? Now I have to explain how I change my data. So the lattice does not change, the pairing does not change, and the only thing which changes is the basis. So I just need to tell you, so when we do mutations, so the lattice stays, the form stays, the basis mutates. So how it mutates? There is a formula for that. So the formula is the following, that you get a new basis. So if you start with old basis Ei, you're going to get a new basis Ei prime after mutation by the vector Ek. And this basis Ei prime is given by the following formula. It is minus Ek if I equals to k. And in all other cases, when I is not equal to k, is given by something which we can call half reflection, symplectic half reflection. So it's Ei plus this symplectic form Ek plus, what is plus I tell you in a second, Ek. So plus is a function on integers given by the rules is either alpha or 0, so it's alpha if your number is bigger than 0 and it's 0 otherwise, so it's cutoff function. And so you take the scalar product, take its, if it's positive, if it's negative, just kill it, and add it to the vector ei. So that's the mutation. And this mutation is equivalent to something which was called Seiberg rule, which was invented, I guess, in 1995 by Nathan Seiberg when he studied n+1 supersymmetric series, but on a different language, so it wasn't lattice as vectors, or rediscovered by Fomin and Zelevinsky. Again, different language, on different equivalent language. They were just talking about encoding your graph by these matrices and telling you how these matrices change. Anyway, so that's somehow crucial thing which I need as an input from this series. And now the fact is that this is kind of fact example. That the action of a 2x2 move on this quiver called Q related to this graph gamma is described precisely by the quiver mutation at the face. So when you have a 2x2 move, you have to say this 2x2 move at some face f. Unfortunately, this diagram disappeared, so I'll draw it again. So 2x2 move is the following situation. You have a graph. It's a part of your bipartite graph. And the graph, it grows somewhere here that I don't care. So all I care about is what happens in this local part of my graph. And then I changed in a way that I keep, as I said before, the red vertices, but the white part is changed this way, and the rest of the graph doesn't change. So this is a 2x2 move. But this 2x2 move is centered at certain face f. So this part of the diagram, I say f. F means this kind of picture. And then after that you get another face f prime described to that picture. And as you remember that this face f produced me some vector in my basis in homology, ef. And so what I'm doing here claims that it's the same as due mutation at this vector. So the action of the 2x2 move on the graph can be described, I mean, can be encoded by the quiver mutation at the basis vector EF. So this way we completely translate the geometry of this bipartite graph to the language of quivers and mutations between these quivers. Is that clear? Or is this far from being clear? Is there any questions about this? That's okay? Okay. Fine. Now, if you are done with this, so I can explain how we quantize after this. So, we get this cluster Poisson, we get this quantum torus. So now we need to do the following. So we have to take, where was this quantum torus algebra on the blackboard? I say it again. So if you have quiver Q, we assign to this quantum torus algebra, which I want to denote by torus, Q-deformed torus algebra related to quiver Q. And if I have mutation from quiver Q to quiver Q prime, then, which is mutation with the center at basis vector EK, then I'm going to produce a map from this algebra, from this quantum torus algebra, the mutated quantum torus algebra. But that's not quite what happened, because you have to take the fraction field. the formula will have denominators. So it's going to be a formula which maps one fraction field to the other, and actually this will be an isomorphism, fraction fields. So what is this formula?
So in the lower one there's a Q and Q prime.
I think there are two different Qs. One is the quiver and one is...
Yeah. Thank you. This is horrible. So from now on, this is absolutely horrible. Quiver, I say quiver C. There's no use for quiver.
And over there is also C prime. In the left board is also C and C prime. So when
Sorry, where did you see?
Yeah.
Here?
Yes.
Yes, definitely. So I'm just changing my mind because you explained to me this presentation.
It's fine, sorry.
Yeah.
This is C and this is C prime. Yes. Okay?
Yeah.
Good. So I'm going to take, and Q is a complex number. One more correction.
Good.
Huh? Okay. So I want to define some automorphism of the field of fractions of the quantum torus algebra. And it's given by the formula that element y from here goes to the conjugation by the Hammer symbol, which we call quantum dilogarithm sometimes. So the formula is like that. So what's important, that this is a conjugation. It's a conjugation by using some function. So this function is Poisson symbol. So psi q of z is 1 plus z times 1 plus q cube z times and so on, times 1 plus q to 5z, and all prime numbers after this. Yeah? Odd, yes, thank you. Odd numbers, yes. I was just checking. So you take the inverse of that, so this is Poisson symbol.
Is the Q missing?
And what?
Is one Q is missing? Because
The first
one
term.
also odd. One Q is odd.
Yeah, this was not intentional remark, Renat, thank you, this actually was. So one is missing, one Q is missing. So I consider conjugation, and it's a kind of beautiful fact that we also put minus here, one, that although this is infinite power series, if you take this y and goes through, then the ratio will be then this divided. If you move it through, then you get rational function in the output. Well-known fact. So we get a birational transformation by using some infinite series, and so. This reminds, like in algebra, we have a theorem that any automorphism of simple algebra is internal. So here what happens is exactly the same, that all automorphisms of the field of fraction of quantum torus algebra, they internal in generalized sense, that they internal sense that we allow also to use this conjugation. But after that...
sorry, capital X is what?
What?
Capital X?
What is capital X? Very good. Remember that when we're talking about quiver, so we said, once again, so the quiver comes with a lattice and a basis and a bilinear form. That's the quiver data. Okay? So you use this and this to hook up quantum torus algebra. It does not depend on this EK. But you use any of these vectors EK to create a basis, to create an element corresponding to this in the algebra, this XEK, because EK is element of element. So now you use this X and take the quantum dilogarithm of this X. Okay? Then you conjugate, so you get this form. Okay. So then one checks that this works in the sense that if you start, for example, with bipartite graph on the surface, which I constructed, and then assign to it this quiver given by the first dimensional homology with intersection form, and then do 2 by 2 move. Then the functions, if they are transformed this way as a quantized functions, when q goes to 1, they will transform exactly as they're supposed to transform the corresponding modular space. And so this is indeed a q deformation of the algebra. But more than that, it also immediately tells you how you quantize the whole story, because all you need to do is this. So we need to take this square C. We start with square C, and we assign to this some Hilbert space. And this Hilbert space is going to be isomorphic to L2 on some R2, some lambda K. And so how you get this K? So you have your lattice with bilinear form. And in this lattice you can use like P coordinates, like P1 and so on, Pk, some basis Q1 and so on, Qk, and some central elements, Z1, so on, ZL. And so those are standard PQ basis vectors. Those are central elements, so they don't influence anything. And then we quantize each of these PQ, as was done in the beginning, so each of these PQ produces L2 in R. And so you take L2 of R to K, where K is the number of these PQ pairs. This, of course, depends. It's like choice of A and B cycles in Bertrand lectures. So this, of course, depends on this choice, but the way it depends is very clear, because that's basically what was addressed in the beginning. So the Yale representation tells you how to relate this. But now we have another quiver C prime, and we assign to this another quiver space, which is isomorphic to L2 of the same R to K, but in a very different way, because it corresponds to different quiver C prime. And this is mutation is the center in the vector Ek. And so now it is tempting to say that we do the same things, that we take like this quantum logarithm of something I'm going to write, xk hat, and say that's what's going on. That's not what's going on. So you're supposed to divide by this quantum logarithm Q check of e to xk hat divided by, now run to flush implementations, divided by beta. And so this is much better, because this is well known to be the non-compact of Faddeev quantum logarithm phi beta of xk. Xk is a variable. Xk is a self-adjoint operator which is given by logarithms of these big coordinates. I'll tell you in a second. It's some self-adjoint operator. And so this function is known to be unitary function. So on self-adjoint, on real line, it has unitary values. And so you can make such an operator. It's unitary. And then you can show that this operator is a intertwiner. So this means that you have lots and lots of Hilbert spaces related to the different C, C prime, C2 prime, and so on, and lots of unitary maps between them which corresponds to mutations, and they form you all together. They give you one Hilbert space with lots of representatives given by this Hilbert spaces corresponding to the quivers. So this is a quantization Hilbert space. Now this Hilbert space comes with the action of some discrete group, which is like mapping class group. So one can explain this as follows. So if you take your surface and apply to the surface some automorphism of the surface, you get another bipartite graph. But as I said, any two bipartite graphs like that, they are related by sequence of 2x2 moves. And so this produces you some intertwiner operator, which tells you how this element of the mapping class group acts. And actually it produces action of the substantially bigger group than the mapping class group. So this way you get some Hilbert space and with representation of the mapping class group. But what is still missing, it's missing that there is some algebra acting on the space. So what is this algebra? So when we start with this quiver and do the sequence of cluster mutations, we can end up with some algebra, which, I don't know, like that, which knows about the initial quiver. And so it's the following algebra. It consists of rational functions well, maybe I say it in a different way. It's given by the following thing. So for every quiver C, you take some element, let's call this element F sub C, which is element of this actual quantum torus algebra related to this quiver. So in simple terms, it's like Laurent polynomial, sum of x1 to alpha 1, x2 to alpha 2, and so on. Maybe some coefficients which are polynomials in Q and Q with integral coefficients. And then you require that if you have quiver C and C prime, they're related by mutation, then these two Laurent polynomials assigned to this and that quiver are compatible. That this transformation takes one to the other. So this is what we call good quantum Laurent polynomials. And so there is some collection of Laurent polynomials in each of these quantum torus algebra which are compatible this way. It's not obvious that there is a single one, because if you look at the formulas, they have denominators. But then one actually proves that in the case we are talking about, there is plenty of them, and there's actually in the space of Laurent polynomials like that, not only that the space is big, and this is as big as it's supposed to be, it's the formation of the algebra of functions, this model space, but actually comes with canonical basis. And so this is the algebra. And finally, so this algebra and its Langland's modular double, what this means. So it acts in this Hilbert space, which we defined, and then we take the Schwarz space. So let's say that we have this S in this Hilbert space with a cluster Schwarz space. This is a common domain for this action of this big algebra. So that's the result of the quantization, and I think I have to finish now to give a lot of time. So the main conjecture which I formulated was the following one. That I take co-invariance of related to sigma of representations of these anomalies. And it's supposed to have canonical pairing with precisely this Schwarz space which is assigned to this data. And this pairing is supposed to be continuous on this variable. And no conditions here, and supposed to be non-degenerate. So right now we defined what this is. And so now I can state the main conjecture. So the main conjecture says that there exists such pairing. And so the last thing I wanted to say about this is that I did this for the case of GLM, and it was sufficient to have one lecture and kind of slowly explain what's going on from the beginning. The same is true for any group G, but very unfortunately, the story becomes very complicated and difficult. This is a big minus of the story, so we don't know how to do this as nicely as this can be done for GLN. This requires lots of work and cannot be explained in one lecture, or in 2 lectures, and 3 lectures. So the case of any group different than SLN and PGLN is substantially, unfortunately, more difficult. But the same results. Okay, that's it.
Questions?
Are there values of the central charge for which the construction is easier?
I can give you the numbers, yes. So in this construction, there was a number beta, and in the central charge there is constant. There is some other constant which is central charge. They are related by the well-known formula. So I can give you this formula. You can find it anywhere. So in whatever paper which discusses two numbers like Planck constant, so beta and central charge, there is this formula that appeared in previous lectures. So this precisely formula for SL2 and well-known analog of this formula in general.
So is the Q related to beta also?
No. Q is exponent of I pi beta.
So it's related to this.
No. There is a beta or some people call beta square the Planck constant h.
Yes.
So this beta or h. And this beta creates you two numbers, q and q check.
Yes.
Now this beta, the question was where is the central charge? If you take beta, then you write standard formula 1 plus 6 times.
Yeah, I see. But they are all related.
I mean,
Right.
beta recalculated the central charge,
Yeah.
it's some formula. I don't want to write it because all of you know this.
Yeah,
But
thank you.
this is the same standard formula which you can write for any group G. Yes.
Just a comment for beta real central charge is greater or equal to 25.
Yeah. So I didn't say this, but if you so this construction, in order to run this construction, I have to talk about some star algebra structure of this algebra. In order to have the star algebra structure, I should have some regimes in which it works, and it works actually in several regimes. In one regimes, if you're talking about this beta squared, it can be positive number. But in other regimes, this beta, I guess, is going to be on the unit circle. And there's two different regimes, and the second regime is not actually star automorphism of my original algebra, but it's only star automorphism of this modular double. So it does not, the first one is star involution of the original algebra, or Q of this X. The second interchanges them. And then under this and only these conditions, as Renat said, there is a star algebra structure. And then what's going on here is a star representation of this star algebra structure. But somehow my goal was to explain that there is this general construction of cluster quantization which starts from a quiver and which is, I would say, to formulate is a pretty simple thing. It turns out that this construction is sufficient to quantize model space of all G-local systems. For me, this is a very big miracle. The miracle is the following. So it's not that may be a big surprise that you can quantize them, but that all of this model space of G-local system has precisely this structure looks like overkill, because you probably don't need that much structure to quantize them. This means, but nevertheless the structure exists. This means that we actually don't quite understand why it exists. It definitely, this is not only the one thing which it does, because the structure is much more rigid than the problem it was presented to solve. And I don't quite understand why it should exist.
So does this also hold if Q is the root of unity?
Yeah, it holds. It's for general. The algebra works for any Q, in particular for roots of unity. If you want to put some star algebra, there are several regimes. So we discussed in this lecture. There is two regimes. There is another regime which is very different than this. These regimes, something like that also holds. But I say again that it is very strange that it's very simple construction. This cluster construction is very rigid because it's sufficient to know one cluster coordinate system and to produce it all. In order to quantize, it seems that it's not necessary to have such a rigid structure. You can do with much less. But nevertheless, it turns out that for all group G and all surfaces, such structure exists. And so I'm saying that I do not understand why it should exist. This means that I do not understand why the structure is there. So it probably has a different destination than the one we just discussed. More rigid than this. It's probably the more rigid setup which is this one.
Another question?
Yeah.
So can this in turn be related to other quantizations like geometric quantization with Goldman's collective or something like this?
That's another story. Yes, but they're not going to touch it. And the way it's
Quantization doesn't exist for that. It is not familiar.
What? We're not.
Geometric quantization site doesn't exist. So nothing to compare with.
Let's take this for the answer. I'm happy with it.
But if you say about Goldman bracket, then it can be derived from this cluster algebra quantization.
Pasha, I did not get it.
So if talk about Goldman bracket and if describe class functions in terms of cluster coordinates, then we reproduce the Goldman bracket, I think.
But it doesn't exist in written. There are no papers about it.
But
there's no paper in archive about this.
But it's written on some old
So
sheet of paper, for example.
Yes, yes, we take this for the answer, so you don't.
Okay, so let us thank Alexander again.
I will continue from with the subject from kind of another end, and really another end, and I will speak also about my favorite toy for the last 2 years almost, which is a Steinberg symbol, and it seems to me that this object, well, I'm also sorry for those who heard my talks about this subject several times, so it's not the first time I'm speaking about that. But it seems to me that the role of the Steinberg symbol is mainly not, well, it's kind of glue, which glues different subjects, and it glues together, well, cluster varieties, and in particular, like mirror space, then, well, it glues conformal cell theory, it glues integrable systems, and some number theory as well. So this is just a mixture of the subjects, and with that well, at least for me, it was kind of understanding that all the subjects are related. So I'll start with defining one. Usually it's not very popular subject, so I would give the definitions. So definition that, well, let R be, well, I will just number 1. So the definition of a Steinberg symbol, so let R be a commutative ring. So the definition will be very formal. And then ring. And, well, R cross is just invertible elements. It's a group. And Steinberg symbol, which I will denote A is a abelian group. Which most of the time I'll imagine multiplicative. So right product is not sum. And then the Steinberg symbol is a map, well, R times R, which I'll denote by curly braces. So these has nothing to do with Poisson structure. This has to do with symmetric structure actually, but not Poisson. But well, it's traditional function. So this is a map from R cross times R cross to A, which satisfies the following properties. The first property is that it's B multiplicative. So AB comma C equals to AC BC. Then it's antisymmetric, but in multiplicative terms. AB times BA equals 1. Antisymmetric is in multiplicative sense. And
Are you sure you want this?
And not what?
Not up to torsion. Are you sure?
Not up to torsion.
You sure?
Well, yes. maybe you will well, maybe I don't understand something, so let me know. And the third one is that well, A B equals 1 if A plus B equals 1. So this is the only property which is really uses addition in the ring. So it's a ring and not a group. So examples. Number 2 examples.
I'm
sorry for my comment. It's not true that AA equal to 1, so that's important. But it's,
yeah, it's not true. AA is not equal to 1. But well, maybe I should add another property that A comma minus A is equal to 1. If R is a field, then it's a consequence of this statement. If not, it's independent property. So will be property number 4. But AA is not 1.
It squares to 1.
But it squares to 1, yeah, because it's plus minus 1. So, and this is very important. This fact that AA is not irrelated.
Bracket is antisymmetric or not?
Yes, it's antisymmetric in a multiplicative sense. So if you replace, then you get something inversed. You need to get used to this multiplicative notation. I'm sorry, this is well. Example number 0 is the following. So if R is R, and then well, I'll denote it by AB infinity. Well, some particular symbol. This means it's one particular symbol is equal to minus 1 if A is negative, B is negative, and 1 otherwise. Well, easy to verify that it's true. For example, if you have two numbers, sum is 1, at least one of these numbers should be positive. So this is number 0. Example number 1. So let our ring be just a ring of rational numbers, and P is a prime number. Prime number. So you can define something which is degree of a rational number, degree of A, no, degree of P to the alpha R over S is equal to alpha if R and S are prime with P. So degree is a number which is positive or negative. It's just degree of a rational number with respect to P. So we can define the symbol A and B, which is equal to minus 1 to the power degree A degree B times A to the power degree B divided by B to the power degree A, and all that modulo P. So all this computation, well, this computation of this ratio should be done modulo P. So if you have A to the power degree B divided by B to the power degree A is something which has the degree of that is equal to 0. Because the degree of denominator and numerator coincide. So this is something which is just the ratio of two numbers prime with P. And then you can compute them modulo P, in the range modulo P. And this, well, also very easy exercise in number theory, well, in elementary number theory, really elementary, to verify that all these properties are satisfied. Well, now something more complicated, and it's more related to what I'm going to speak later on. This is number 2. So let R be a functions maps from functions from a circle which I will imagine R quotiented by 2 pi z, which is just a circle.
Sorry, for the second property you have to say A is not B. Is A not equal to B?
Sorry.
Second one.
Second property.
Because if I put A equal B, so it's
A times AA equals 1.
Is it okay?
Is it okay? But AA is not equal 1, but the square of it. So it can be, because A for example, A minus A, sorry. How to say? A minus A, A minus, well, yeah. This one is equal to A minus 1. And this is equal to 1. So therefore, AA equal A comma A minus 1.
Just to make sure, in the third property, A plus B is equal to 0 or to 1?
Equal to 1.
Equal to 1, yeah.
Equal to 1, yeah. Well, if it's equal to 0, then it's also 1, yeah. That's it. So you have a map, the space of function, just complex function on a line. So R cross is just maps, well, smooth maps, for example, R to 2 pi z to C star. And also the same thing, you can define something which is called degree. So degree of f, if f is in R, then you can define the degree of f is just how many times f goes around 0. If you have an element which goes to C star, so it goes around 0, you cannot touch 0. So this is, well, formally you can write down as 1 over 2 pi I, the integral of d f over f. This is just the number of times it goes around 0. And then I write the most complicated formula, maybe, but the most important formula, which is the symbol, the formula belonging to Bayesian sum. And the formula is the following. So if you have two functions f and g, then you have the symbol, which is exp of integral from x to x plus 2 pi. So integral of the period log of f d, 1 over 2 pi I. D log of g times, well, this integral is not well defined because, for example, because log f is, well, depends on x. Because log f is not a periodic function. It's not a function of a circle. So, but if you correct this function a little bit, namely you take g of x times minus degree of f, then this function doesn't depend on x. So this is well defined, doesn't depend on anything you can imagine. Doesn't depend on x, doesn't depend on branch of logarithm, doesn't depend, and, well, just well defined. You will see in a short while, perhaps, where this comes from. It's just certain monodromy of certain connections, some non-trivial line bundle. But this is the formula. Well, the fact that this function satisfies all these properties, so I'll just. So all those properties, well, the first property is more or less obvious because you have log f d log g, log f, you take, you can see it's more or less obvious that this is the case. You can take the computation, the second also. The third one is also not very complicated to verify. If you like computations, you can verify it straightforwardly and just compute this integral. If f is plus g equals to 1, then you get something which is actually a dilogarithm, and the analytic properties of dilogarithm show this thing. But this can be proven even simpler, not so straightforwardly. So this is. Is
it x independent?
It's independent on x, yeah. It's just exactly why I need this correction. Sure. So this is well, another symbol is a little bit more, well, kind of more complicated, but I want to speak about that because it's kind of the most complicated symbol which I can imagine. So let's consider the space C star cross C star. Cross C star. Maybe I will not speak about that in all details, but well, C star cross C star, on C star cross C star, for example, if you have here the F will be and G, where there are just coordinates on C star cross C star. So just elements here is just a pair of numbers, F and G. And consider the form log F d log G. And of course, this form is not single valued because log F is not single valued. But on the other hand, well, 1 over 2 pi I. Alpha. At alpha is a connection form. On a line bundle E. So you can just define the line bundle E is such that this form is a connection form for that. Well, once again, I don't want to spend much time defining that. Well, you have this bundle E. Another version of that, you have a Heisenberg group H, which is the space of matrices A, B, C, 0, 0, 0. It's a Heisenberg group. And then you take H with complex coefficients, and you quotient it by H of integer coefficients. And this quotient is just the total space of your line bundle. It's another definition of this line bundle over C star cross C star. What's amazing that this line bundle E is not algebraic. Is not algebraic. Because all algebraic bundles on what's called C star cross C star are trivial, and this has Chern class equals to 1. So this is the only non-trivial line bundle. But this line bundle has a connection. And this connection, so yeah, and then we have, now I will define the symbol, and the symbol is the following. So you have R is equal to, well, X is an algebraic variety, or not necessarily algebraic, just variety. Complex variety. R will be just the space of functions on X, the space of regular function on X. A will be the space of line bundles on X with connections. And line bundles with connections on a variety is a abelian group. You can tensor multiply them. So it has a structure and then I can define the symbol omega of A and B, which will be equal to, I consider AB, the pair of AB can be considered as a map. So this belongs to the map from X to C star squared. And I can just pull back my line bundle. So I have a line bundle on C star squared. I can pull back the line bundle, and then well, it's maybe the most complicated definition of a symbol, but well, once again, we can verify that everything is the symbol. There is a now finally, it's number symbol number 4, the same thing is R equals O of X, and omega, and A will be just close to forms. Two forms on X. And the symbol AB, maybe I should denote it by omega, is equal to, it will be symbol which I'll call it, sorry, right, omega, but the symbol AB. Put B for Benenson here. Yes?
Can you re-explain the pullback, please?
The
pullback?
The pullback, so if you have a line bundle on C star squared, if you have this is again from X to C star squared. So you have a map from one manifold to another, from X to Y, you have a line bundle on Y, you can pull back this line bundle to X. That's just that.
And what happens with connection?
Pardon? With connection, you have here you have connection. You pull back connection as well. Line bundle with connections is a contravariant functor with respect to yes. So AB omega is equal to just d log A d log B, and this is 2 form. And of course, here the A is, I drew it straight A because it's not a multiplicative group, but an additive group. Of course, the group of forms is additive group. So you associate two functions, you associate this form, and of course this is, well, it satisfies all these properties. Once again, these properties are very easy to verify. The last one is absolutely trivial because for example, if you have d log A d log 1 minus A is obviously 0. So this is it. So what is relation? It's actually, all of them are related. And the relation between them is, so now the number 3, a relation between symbols. Between symbols. The relations between the symbol number 1 and symbol number 1, which is this one. Oh, sorry, I should enumerate this by Roman numbers. Otherwise, it's a relation between 1 and 2. So you have this horrible formula, and here you have something which is just very, very simple. So they are maybe sorry. I'll denote this one by the letter B. Sorry, and here I'll put letter E because it's a line bundle. So this will be.
So
which is just next letter after B.
For the last two examples, is it trivial what R star is? So this inverse elements?
It's just invertible functions. Just invertible function of the functions with value at C star.
Okay. And the 2 form is close, but it's not exact. Can be exact?
It's not necessarily exact. Because, for example, this form, just on C star, you take d log f d log g, it's not exact. Because this is integral over the cycle is equal to 1. And this is just first term.
It's essentially never exact.
It's never exact.
It's never exact. It's never exact. So, what's the relation? Somehow, kind of amazing relation between the symbol So if you have the, what's the relation between 2 and 1? It's not a relation, but kind of analogy. The 2 and 1 are very simple, and the observation is the following: that, so 2, 1, 2, 2, 1. The observation is the following: that if you take the integral, let f and g be two holomorphic functions. Meromorphic, well, functions with isolated singularity at the point P. So holomorphic, well, functions, analytic functions.
You mean that it's on the circle, when in what sense?
Right. Just one thing. And I can define the symbol as following way. So, and gamma is just a path around P. So gamma is a path, well, it's just, you have the point P, and you have a path around. So this is just this path. So let's define, by definition, the symbol Fg. Gamma will be F restricted to gamma and G restricted to gamma. So this I get numbers on, well, function on a circle, and then I compute the symbol using the old formula. So roughly speaking, I can compute this integral not on the circle, but the circle embedded into complex plane. And that, so therefore, well, and I claim that this is equal to, I have no space, sorry. This is equal to minus 1, minus 1 to the power degree F degree G times you take F to the power degree G divided by G to the power degree F, and then you compute it at the point P. So this time, well, degree F degree G is the same story. So for example, if F and G are meromorphic, degree F and degree G are just is just the order of the pole at the point P. So you take this ratio, the order of the pole of the numerator equals to the degree of the pole of the denominator. You take the ratio, you get a function which is non-zero holomorphic at 0, and you can at P, sorry, non-zero holomorphic at P, and you compute this value at P. It's number. Pardon?
P is not prime here.
No, P is not prime, but somehow it's analog to this prime. It's just not by. Just do it on purpose. So this is the same, essentially the same formula.
Example 3, or
It's, I want to say that example 2 and example 1 are related because they are analogous.
But they are just rational numbers.
Here is just in Z over PZ.
But AB also rational numbers. So
here AB are rational numbers. Here F and G are rational functions, or rational or modulary. I mean that the same formula, if you wish. Well, it's just once again, it's not just a particular case. It's just an analogy. Maybe you can make it more precise, but I don't want to. But it's given by the same formula. In particular, well, will be very important that in particular, if I take the bracket, the f z minus p with respect to a circle around p, this is equal to f of p. It's just a particular case of this formula. So you just take the value of f at p, it can be computed in this sense. Now, what is relation between 3 and 2? Well, I'll just do this is a monodromy. So you have a line bundle with connection. Suppose you have two functions, f and g, on a circle. So therefore, you have a two functions on a circle gives you a map from a circle to C star cross C star. And you can compute monodromy along this path. And this monodromy is given exactly by this formula. So this formula comes actually from this construction number 3. If you didn't understand that, you can just take this formula, but...
Actually, historically, this is not exactly the case, but okay.
Historically,
this formula was invented by Williamson.
Right. And this construction belongs, E belongs to Deli. I think it belongs to Deli. No? I don't know.
This belongs to Ramakrishnan.
Okay. Well, maybe, yeah. So this is so it should be denoted by R, so not E. So, okay. So this is given by monodromy, and of course, from 4 to 3 is just a curvature. So if you have a line bundle with connection, then you can take this curvature and get the 4. This is, all of them are kind of related between each other. So, well, now the question is what I'm speaking about. Well, it's nice, but what is the relation to clusters, to well, conformal field theory, integrable systems, and all whatever. So the subject number 4 is the following. So Sasha was speaking about coordinates on moduli space of flat connections, local systems, and while particular case of this SL2, it corresponds to and if you corresponds to if you consider real numbers as a field, positive real numbers as a semi-field, whatever, you get a Teichmuller space. So there is a coordinate. Well, this is the space which Sasha was speaking, x of sigma SL2 is isomorphic to C star to the power, variational isomorphic to C star to the power 2 power n. There are coordinates. But there is another space which is called A sigma SL2, which is isomorphic also to the same thing. And just, I don't want to spend much time about that, but roughly speaking is the following. So what is A of SO2? So we have a Riemann surface, but you do not allow holes in it. So you have punctures here. You have punctures, and you have connections such that these are unipotent monodromies. The monodromies are just around the points are unipotent. So if it's matrix is unipotent, it means it preserves plenty of vectors. So there are eigenvectors with eigenvalue 1. So if you choose at every point, you choose a vector, eigenvector of monodromy with eigenvalue 1. So you can, you have two, and you have triangles. Then you can just vector multiply, there is two-dimensional space, you have vectors, you can take wedge products. Well, there is a problem with signs, let's put it under the carpet, but you have here, for example, I don't know, V1, V2, V3, you can take V1, wedge, V2 on this side. This is a number, because you have two vectors in two-dimensional space, this is determined. And these are called A coordinates. And the space of such monodromies plus vectors at every punctures. It can be generalized for any group. So you have these coordinates, and these coordinates have the property that, well, and these usually are, well, this is an A space, so the coordinates are called by the letters A's. That's the main reason why it's called A space. So you have this is A1, etc., AN. And, well, for any triangulation, you can construct a quiver, like Sasha was describing. In this particular case, I will just consider example SL2. The quiver will be the following. So it should be red, as Sasha was. You have variables attached to the sides of the triangle, and so you have the quiver, which is something like that. And if you flip a triangulation, then there is a rule how the coordinates change. So it means if you flip one triangulation, for example, AK, which is well, the coordinates here, and on the flip triangulation, well, AK, on the flip triangulation, so AK prime, and you just take, instead of that, you take this one. This is AK prime. AK prime is equal, and the formula can be written in the following way. So this is product, the 1 over AK times the product over all arrows from I to K of I plus product from K to I of AI and over AK. Here is the formula how you change the coordinates. If you change triangulation, you change coordinates. So this is this formula. It's not exactly the same coordinates that Sasha was explaining. They are kind of dual ones. Moreover, it's coordinates of a different space. So, but I work with these coordinates. You know, there was kind of well, always Famil Zelevinsky preferred these A coordinates, and Sasha and me preferred the X coordinates, and then finally there is a peace, it seems to me, because both of them are well, so I will speak, Sasha was speaking about X coordinates, I will speak about A coordinates, so this is another version. So the claim is the following. Well, why I defined all that? I claim the following. Claim, if you take omega, which is the product over all arrows, once again I need to read, over all arrows, or my quiver, ij, of the symbol of ai, comma aj, times the product of all i's of -1 ai is invariant under mutations. So if you have, for any symbol, so you take, for example, how you can use this formula. You can assume that you have all your coordinates are rational numbers. If all your coordinates are rational numbers, you have a point, for example, a rational point in Teichmüller space. And so for any rational point of Teichmüller space, for any prime p, you can construct a map to z over pz. So this is, well, somehow you split your Teichmüller space into parts according to the modulo p, which is, well, kind of was surprising for me that I realized this is the case.
rational part of Teichmüller space.
Rational points of Teichmüller space are split according to the, well, of course, everything can be generalized instead of the field of rational numbers. You can take number field and well, whatever. It's can be done for very generalized.
And sorry, which of them exactly called a Steinberg symbol?
Well, Steinberg symbol is just Steinberg symbol is this map which you have a ring, and for every ring. No, I say that if you take any Steinberg symbol, if you have it, well, of course, you have your cluster variety. For example, you have your coordinates in some ring, in whose value in some ring. So if you have a symbol for this ring, a symbol, it can be could be different. For example, for rational numbers, you are as many symbols as prime numbers. So if you have any prime number, you get some invariant, something which doesn't depend on coordinate system. So you compute it for one coordinate system, and then it automatically takes the same value for another coordinate system. For example, this thing, well, you can compute some number which doesn't depend on coordinate system. Particularly, it means that mapping class group invariant. So it means that you split not just your Teichmüller space, but you split your modular space. It's just invariant under mapping class group. It's always, the problem about these cluster coordinates with regulated coordinates on the Teichmüller space is that it's very difficult to find some object which is invariant under mapping class group. Usually, well, there are few of them. And one of them is symplectic structure, which is, in fact, invariant. But somehow you can generalize the notion of symplectic structure, because if you, for the symbol, you take the symplectic form, d log A, d log AI, d log AJ, you just get symplectic structure, Bell-Peterson symplectic structure. Somehow, this number mod P is just generalization of symplectic structure. So this, in general, you should look at the symbol as just generalization of symplectic structure. So in particular, in particular, the consequence is that the product, the sum of it's very classical statement, d log AI, d log AJ over all arrows IJ is invariant. Is an invariant form. A mapping class group invariant form. Which is actually Weil-Peterson form. So this is in relation to clusters, but there will be another relation to clusters. We'll think about later on. Okay, now I'll come back to some relation to conformal theory. Also some elementary part of it. I don't want to erase this one.
With clusters, this is true for any cluster variety.
This is true for any cluster variety. I gave an example just because we were speaking mainly about Teichmüller space. I don't know, Vladimir theory. So that was my example. But for any cluster varieties, it can be like that. A moment, I should decide what to erase. Maybe I will erase number 4. What definitely needs this Bayesian thing? I mainly use this formula. So actually this symbol is something which I kind of wonder why it didn't appear earlier in conformal theory for the following very simple reason. Because the claim is that the symbol Fg, which is, Bayesian symbol, is a cocycle on the group the group of functions on a circle. So let's define that just H will be this map of R. I'll denote by this by H. On the group H. And this cocycle is just a billion cocycle. Usual cocycle that you have on a billion, a billion Heisenberg group. So Heisenberg, this is a group corresponding to Heisenberg algebra. Yeah, this is cocycle, but it's a group cocycle, not algebra cocycle. So in particular, one can define so it means that we can define a central extension of, using the symbol, you can define the central extension of H. This is equal to 1, C star, 1. Sorry. And what is H hat? Well, since you have a central extension, so let's fix a map from H to H hat, which is not homomorphism, of course, which, well, traditionally is denoted by double dots. And, the multiplication, what is H star? This is a space of pairs X times F in an H. So any element here is just the product of image of H and some complex number. And the multiplication, let's take H, let's define the group H plus is the functions which are, you have circle here, but let's take the circle, identify the circle with the unit circle. So it's just a spatial function f such that f is homomorphic. Is homomorphic inside, morphic, non-zero inside the unit circle. And H minus, have no space, I continue here, H minus will be the space of functions which are zg to the k, z to the k times g, where g is holomorphic outside z equals 1 and limit of, g of infinity is equal to 1. Whatever. Some normalization, some splitting of my group into two parts.
What is x here? I'm confusing. It's x. Say x double dot f. What is x?
X is a number. X is a complex number.
So it fits x?
No, sorry. What is H hat? Hat, sorry. H hat. What is H hat? It's central extension. So any element of the central extension is a product of image of H times image of something here. So X is an image of element here. So X is here. So in order to span all elements of H hat, you need just to take the product of something coming from here, something coming from here. Just splitting of this exact sequence, but so this is it. And the product will be X times maybe F times G now. Therefore, any element F, it can be equal. Maybe I should write it. More precisely. H minus H plus hat will be just C star times H plus. Like that. So the element here are the x times f plus. So it means that f is a plus function times a number. And H minus will be just, that will be the image of H minus. So inverse image of H minus. Now I define the product Fg as the product of I forgot to mention that any function, of course, any function f can be decomposed in a unique way into product of plus function and minus function. So it's f plus times f minus. So it's just definition of a plus is plus part of function, minus part of function. So fg equals f plus g minus times fg.
I'm sorry, in the definition of H minus, we consider all negative case, or?
So it's just, well, if you, yeah, it's just, well, if you wish, it's a Laurent series with respect to 1 over z. Well, power series in 1 over z, it's power series of over z, but the one difference is that I require that it's equal to 1 at infinity. And also I take this power stuff, I just put it into H minus, not H plus. Well, it's just some technical details, whatever. The idea is just you have this product. And I claim the following claim, that H hat is something very, very simple, that H hat is just the Heisenberg group. The key word here, this is a group, because usually you, well, wrote million of times in Heisenberg algebra, but this is a just well, you take the exponent of that. This symbol is nothing more, nothing else that this Heisenberg algebra. Okay, I will erase this one. Which time we have? Now this Heisenberg algebra has a representation, and also the standard representation, which you know very well, but also the standard representation of Heisenberg algebra, you usually use it, use formula for the algebra, but not for the group. But what is the, so the number 5, this is a representation of H hat. And it also can be written down in terms of symbol. Now induce, well, we have a representation rho, which tells H hat plus to C star, which sends X times F sends to X. This is just a representation of this algebra H hat plus. Now you can try just take the induced representation for the whole group. So induced representation of H hat. What is an induced representation? Induced representation is actually the space. What is a definition of induced representation? You take H hat, you take the functions. So, well, maybe I can write just a formula or whatever. Well, the space of space, what is the representation space? The representation space is is just the space of functions on a quotient. So functions be functions on H hat quotiented by H plus. Which I identify by H minus. well, hat, actually, this is isomorphic. H hat minus is isomorphic to H hat, it doesn't matter. And what is H hat minus? H hat minus is just the space of functions with negative. So this every function on H minus is a space of functions of the type z to the k, e to the sum pk t to the minus k, z to the minus k, k is positive. So any such function can be written in the following form. Tk. So therefore the H is isomorphic to the k, t1, t2, etc. So this this one integer and many complex numbers just coordinates on my space H minus. So therefore my space of in this representation is just a space of functions on the of this variable. So the space variables k and then many variables t. And you can recognize that this is a function which is very well. Tau function is actually the function of the same variables, and essentially this is related one to another. Where is the eraser? Now I can write down explicitly the representation. So if you have an f, well, the formula for this representation is the following. If you take the function f and act on so let's V be an element. It's B for Poissonic actually. Let's take V some function here. So f acts on V, which can be computed on some function G minus, where G minus in H minus. So if you compute what is the definition of this representation, is the following. You take the symbol of Bennington symbol of f plus G minus times V of G minus F minus. So it seems to me very simple formula. So you take G minus F minus is just minus function. So you take F, decompose into two parts, positive and negative. You multiply the argument by the negative. So you stay in negatives. And then you multiply it by the symbol F plus G minus. So this is a example. Let's take F plus, well, consider the following situation. This is the disk, it's a unit circle. Here you have point A plus, A minus, sorry. Here you have point A plus. So you have 2 points. A minus and A plus. And let's compute the operator of, well, corresponding to x minus z minus A minus divided by z minus A plus. V of G minus. Represent this thing as a composition of, well, I just want to apply this formula. So the positive part, well, z minus, z minus a plus, minus is equal to z minus a minus. And z minus a plus plus is equal to, sorry, z minus a minus divided by z minus a plus. Plus is equal to 1 over z minus a plus. So therefore, you can easily compute the answer, and this is equal to z minus a, 1 over z minus a minus a plus, g minus times v of g minus times z minus a plus, a minus. Well, and on the other hand, this is equal to z minus a plus g minus z minus a plus v of g minus a minus. Why I did so? Because the symbol has the property that I inverse. The symbol is inversed. And I did two inversions. First of all, I replaced z minus a plus by 1 over by z minus a plus, and then I exchanged the argument. So they changed the sign twice. And this is equal to z minus g of a plus times v of g minus a minus. So this is a simple formula how this operator acts on my function. But what is nice about this formula, that I can take a limit of that. And the limit that psi A equals the limit, then A plus and A minus tend to the same point A, which is of course the point on the circle of z minus A minus divided by z minus A plus. And I claim that psi A satisfies the following relation: psi A psi B plus psi B psi A equals 0. And this is, well, using this formula. So psi A is equal to psi A epsilon of V of G is equal to G of A times V of G minus of V minus A minus. It's product, it's not a constant. So, well, the formula is very simple. You can very easily verify it. So actually, it's just the boson-fermion correspondence. I want to say that you have fermionic operators, and the fermionic operators are just nothing but expressed in terms of bosonic operators using just this function. The only thing you need to have some transcendental think that you take a limit, then A plus tends to A minus, because this is a actually the function psi A is a function. If you take what is the function psi A? The function which is what is the limit of this function? If you take a logarithm of psi a divided by 2 pi I, so this is a function which is equal to 0 until a certain moment, then it goes to 1 and continues as 1. The exponential of this function is single-valued. And it's just, well, in the limit, it's just step function. And these step functions correspond to fermions. And to verify it just takes. Well, I think I'll stop here. I want to say that well, there is a very simple formula. Well, if you, instead of 1, you can pass to Riemann surface, put several points here, and in every point you have your representation, the space representation of H, and you act by homomorphic functions in the complement to these points, and take the invariant operator, so you get just get tau functions. So this is one of the ways to define tau functions, kind of simple. First of all, because you work with group and not with algebra, because invariance with respect to algebra doesn't give you the formula, explicit formula for that. Here you have a group, and this is much easier. So, so the moral of the story is, the moral of the story is, what Newton considered his main invention of his life, that he discovered that it's useful to study differential equations. But to solve differential equations, yeah. So here it's useful to use symbols. So thank you very much.
Questions? Is there? So this Beilinson co-cycle, it looks a lot like the Bosch co-cycle on the diffeomorphism group instead of the
well,
are there
I
any
think
relations?
it's related. They are certainly related, but what diffeomorphism group acts on the space of functions on the circle, but it's kind of abelian analog of co-cycle. So, diffeomorphism group is much more complicated than the group of functions on the circle. So,
any concrete relation between, for example, the central extension that you have and the Virasoro group central extension?
I think that I cannot write explicitly, but once again, the Virasoro group is much more complicated objects. Here, the idea is that the object is very simple, just functions. Of course, on this function, you have an action of the diffeomorphism group, and then if you lift this action on the space, the representation space, you get the action of the Virasoro group, and then you can write down the corresponding cocycle. So this cocycle induces the Virasoro cocycle, of course. It's just, I didn't touch the complicated things. I tried to speak more simple things.
Is there a generalization of this Beilinson formula to the case where Fg are grouped with values in, I don't know, SL2?
The answer is yes, but not generalization really. You can take the loops in SL2 and express the cocycle for loops in SL2 in terms of Beilinson cluster. And for that you need really to use cluster variables. So you take SL2, you introduce cluster variables on SL2, and then on this SL2 you have this symplectic form, and then you just you take the symplectic form on SL2, well, not symplectic but close to form on SL2, and then instead of close to form, you consider it as a symbol and substitute the functions with values, or functions. You replace symplectic form, but by Beilinson cocycle, and you get a cocycle Poisson. So this is also can be done, but other way around. So
for SO2, not for loops in SO2.
Well, you obtain something with loops because you replace your coordinates on SO2 by functions in a circle. So automatically, instead of SO2 five-dimensional, you obtain SO2 loops.
It looks like too simple to be traced. In a sense, I thought that it is rhythm determinant, this in this case. At least it was written in some papers that it is a cocycle that describes a cosmology group, which we should obtain in this case.
Well, it should coincide. I cannot verify that this coincides, but it should coincide. I do not doubt. Actually, the formula which I obtained is just it's Kubota formula for the cocycle, literally. So this is a cocycle written actually. Well, if you consider SO2 over Q, then you can obtain the cocycle of the group for the group SO2 QP. Yeah, the same formula works actually for if you replace the symbol, this P symbol by Bellington difference, you get the cocycle for. Well, but there are some. Well, I would say that I didn't speak about that also because there are some technical difficulties there. So I cannot state that I know it for sure.
Are those cocycles computable in some explicit way? In a sense, if you take some explicit elements of the loop group, can you compute them?
Yeah. If you give me an element of the loop group, I can compute the value of two elements of the loop. I can compute the value of the cocycle. And also you can compute the third cocycle actually for the loop. So this is the whole story about these cocycles. But here is just the elementary part, but even the elementary part gives something. Yeah, I think to me that's amazing for me.
Are there limits to this, or can we also do it for elliptic algebras, for instance?
What was the question? Well, what about elliptic algebra? I have no idea.
This really looks like the OPEs in W algebras, like elliptic W algebras, for instance, the kind of formulas you wrote.
Once again, it's just a billion something. So a billion Cosmodi. So this is very far away from W algebra somehow. Well, even Virasoro is not sitting very, very closely.
But in principle, if there are cluster coordinates, then one can reconstruct things.
Yeah, if you have cluster variety, you can just study cluster variety over, you replace the numbers by the functions, for example. So it means that you have paths, loops in cluster varieties. And in loops of cluster varieties, you have some for any loop, you can associate a number. So it's kind of cool.
Questions? So I probably have a question I can't resist asking. We just been taught how to quantize the space of flat connections. So can you put the symbol there? Like
well, what's the relation to quantization? It's the question which Sasha answered more or less by saying, postponing it. It's relation between geometric quantization and deformation quantization. So the idea is that this story, for example, I described more or less the construction of line bundle over any cluster variety. And this line bundle over cluster variety is kind of pre-quantum line bundle. But pre-quantum line bundle for very particular value of quantization parameter of this h equals to 1. Not 0, but h equals to 1. H is just some self-dual point, which is kind of distinguished, where q equals to 1 also, so it means it's commutative, but still quantum. And so this is geometric quantization for h equals to 1. But how to generalize it for h different to 1, it's, I can say that just I have some ideas about that, but better not to say because they are definitely not finished. systems in cumbersome, but we can discuss.
Quick.
Okay. When you said about cluster coordinates for SO2, did you mean SO2 or roots of SLN?
No, cluster coordinates for SO2. You take cluster coordinates for SO2, so just 3 variables. And then you replace the 3 variables by 3 functions on the circle. Or 6 variables, because you have 2 copies of the SO2. To write cocycle is function of 2 meters.
Precisely. Is it simple or not?
It's simple, but maybe better to write it to you explicitly. There are some technical differences also, but.
More questions? Okay, if not, let's thank the speaker again.